There's a line in nature where physics doesn't just get difficult, it breaks, and the universe enforces it with gravity. Push for more precision, look closer than close, and reality doesn't sharpen into focus. At the Planck scale, why does the act of measuring space and time risk creating a black hole? And what is space-time hiding when our best theories fail? Every successful theory we trust is written in a language that assumes space-time is already there. Quiet, continuous, obedient. Yet at nature's smallest scales, that assumption may be the first thing to fail. We have learned to interrogate reality by sharpening our questions, turning resolution into a kind of power. Each new instrument has translated smaller distances into higher energies, and higher energies into deeper structure. That method built modern physics, atoms, nuclei, quarks, and a vacuum that is never truly empty. But the Planck scale is where our usual bargain collapses, because the arena of the experiment becomes part of the experiment. In quantum mechanics, uncertainty is not ignorance but a rule, and rules can be quantified. In general relativity, gravity is not a force added to space and time, but the geometry that makes distance and duration meaningful. When those two principles collide, the familiar tools of calculation begin to produce the same warning in different disguises. One side demands a fixed stage to define fields, energy, and time evolution. The other insists the stage is dynamical, shaped by whatever energy we try to localize. Push the mathematics hard enough, and the results stop being merely difficult. They become ambiguous, divergent, and at times self-contradictory. So this film follows a strange boundary where precision, curvature, and uncertainty tighten into a single knot. It is a boundary marked by three constants, C, H, and G, whose combination defines a scale so extreme it sounds almost fictional. The Planck length is not simply smaller than anything else. It is the point where our definitions of measurement and geometry begin to fuse. To understand why physics breaks there, we will rebuild the wall from first principles and watch how it rises. We will see how the very act of probing a distance becomes inseparable from injecting energy, and how energy becomes inseparable from shaping spacetime. We will confront what happens when a smooth manifold is treated as a background assumption, even as quantum fluctuations insist the background cannot stay still. Along the way, we will pass through places where the universe keeps meticulous accounts, yet the ledgers refuse to agree. Singularities appear not as exotic objects, but as theorem-level signposts that the equations have outrun their domain. Horizons behave like thermodynamic surfaces, carrying temperature and entropy, and they force a question that sounds philosophical until it becomes mathematical. And then the tone shifts, from breakdown to blueprint. If space-time is not fundamental, what could it be instead? A lattice of quantized geometry, a network of relations, a string's vibration, an error-correcting code written in entanglement. Different approaches speak different dialects, but they may be pointing toward the same underlying grammar. This is not a story about adding one more equation to finish the textbook. It is a story about what must be redefined when the smallest distances refuse to behave like distances at all. At the Planck scale, the universe is not merely difficult to describe, it may be telling us that space and time are emergent answers, not primitive facts. One guiding idea will return again and again. At the deepest level, the crisis is operational. What does it mean to locate an event, to compare two clocks, to separate cause from coincidence, when the concepts doing the measuring are the concepts being measured? If we can decode that, we do not just tame infinities, we replace paradox with a new, coherent story of gravity in the quantum world. And the most unsettling part is this: the Planck scale is far beyond our machines, yet it may still leave fingerprints. In delicate tabletop experiments, in the quiet statistics of the cosmic microwave background, and in the ringing aftermath of colliding black holes, nature may be offering hints, subtle, testable, and easily missed, about what spacetime is made of. So we begin with the smallest question that can be asked, then follow it to the edge of meaning and beyond. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across 7 chapters, we will derive the Planck scale, confront the measurement trap, and explore foam, horizons, and quantum information. Finally, we will look for experimental and cosmic clues that could turn this boundary into evidence. Start with a simple demand. Show me what is smaller than anything we have ever seen. Picture a dark laboratory, quiet except for the hum of power supplies and cooling pumps. On a screen, a faint dot sharpens, then blurs, as if reality itself refuses to hold still. In everyday physics, the strategy is straightforward. To see smaller details, you use a shorter wavelength probe, and that means higher energy. Light microscopes improve when you push toward blue and ultraviolet, because shorter waves diffract less. Electron microscopes go further by using matter waves, where the de Broglie wavelength shrinks as momentum rises. A microscope improves by tightening the beam. A particle accelerator improves by raising the collision energy. Precision comes from paying the energy cost. That logic is not just engineering folklore, it is built into wave physics. Any probe that behaves like a wave spreads when it passes an aperture, and the spread sets a hard limit on resolution. Now push that logic until it stops being helpful. Imagine you want to resolve a region smaller than an atom, then smaller than a nucleus, then smaller than a proton. Each step forces the probe to carry more momentum because the wavelength has to be comparable to the size you want to distinguish. Quantum mechanics says that momentum cannot be localized without spreading uncertainty elsewhere. This is the Heisenberg uncertainty principle in its operational form. If you demand a smaller position uncertainty, the momentum uncertainty must grow, and the probe becomes more violent by necessity. So you raise the energy again, because you want the uncertainty to shrink. You aim for a tighter focus, a cleaner answer, a more definite position. At first, the world cooperates. Higher energy reveals quarks, gluons, and the restless vacuum of quantum fields. In the 20th century, this was not a metaphor but a method. Rutherford's gold foil scattering used energetic alpha particles to infer a tiny nucleus, and later colliders mapped the proton into partons that became quarks. As the energies rose, new layers appeared like hidden gears. Jets of particles traced the presence of quarks and gluons, while detectors turned invisible interactions into luminous tracks and timed flashes. Even emptiness stopped looking empty. Quantum field theory predicts that the vacuum is the lowest energy state, yet it still seethes with fluctuations that can briefly borrow energy within uncertainty limits. Then the strategy backfires. The energy you concentrate into a tiny region becomes a source of gravity. General relativity treats energy and momentum as the substance that curves spacetime. If you pack enough of it into a small enough volume, spacetime responds violently. This is not only about mass in the everyday sense. In Einstein's equations, pressure and energy flux also contribute, so a concentrated beam of radiation can curve geometry too. The thought experiment turns into a trap. The act of measurement can create the very thing that hides the answer. If your probe energy is high enough, the region you try to resolve can form an event horizon. The information you wanted to extract gets sealed behind a boundary. An event horizon is not a physical surface you can touch, yet it behaves like a one-way membrane. Light cones tip inward, and every future-directed path leads deeper, away from outside observers. This is the boundary in nature where asking for more precision stops producing better knowledge. The universe answers back with a black hole. That boundary has a name. It is the Planck Scale. The Planck length is about 1.616 times 10 to the minus 35 meters. The Planck time is about 5.39 times 10 to the minus 44 seconds. To make those scales feel less abstract, compare them to what we know. A proton is about 10 to the minus 15 meters across, so the Planck length is smaller by 20 orders of magnitude. The Planck time is even more alien to intuition. Light itself, the fastest signal we have, would cross a Planck length in one Planck time, and even that statement assumes spacetime behaves smoothly. These numbers sound arbitrary because they are so far from human scales. They are not chosen by convention, and they are not tuned to any experiment. They are built from nature's constants. Combine the speed of light, Planck's constant, and Newton's gravitational constant, and the units collapse into a length and a time. Historically, this idea goes back to Max Planck at the dawn of quantum theory. He noticed that with c, h, and g, nature offers a set of units that do not reference any human artifact. That construction matters because it signals a regime where quantum effects and gravitational effects are equally unavoidable. It is not merely small, it is balanced. At the Planck length, quantum uncertainty insists that localization cost enormous momentum. At the same scale, gravity insists that enormous momentum warps spacetime into horizons. The result is not just technical difficulty, It is a collision between the rules that define what a measurement even means. To understand why, we need the two pillars that built modern physics. Each pillar is internally consistent, experimentally verified, and conceptually stubborn. The first pillar is quantum mechanics and its field-theoretic extension. It says nature is described by amplitudes, superpositions, and operators, not definite trajectories. In quantum language, you do not predict a single outcome, you predict a distribution. The wave function encodes probabilities, and measurement selects one result while leaving deep questions about what selection really means. Uncertainty is not a flaw in instruments. It is a structural statement about conjugate quantities like position and momentum. The mathematics makes that structure unavoidable. Position and momentum operators do not commute, and the non-commutation sets a lower bound on how sharply both can be specified. Quantum fields fill space even in apparent emptiness. Particles are excitations, and the vacuum is an active state with fluctuations. Those fluctuations are not just philosophical decoration. They shift energy levels, as in the Lamb shift, and they generate forces, as in the Casimir effect between closely spaced plates. Quantum theory also assumes a background stage. Even when fields fluctuate, they fluctuate on spacetime that is treated as given. You choose coordinates, define time evolution, and write down commutators on slices of space. The geometry can be curved in some settings, yet it is usually fixed rather than fully dynamical. The second pillar is general relativity. It says gravity is not a force in space, it is the geometry of space-time itself. This was Einstein's radical step in 1915, built from the equivalence principle and the demand that physics look the same in all frames. Gravity became curvature, and free fall became the straightest possible path. Mass and energy tell space-time how to curve. Curved space-time tells matter how to move, and horizons emerge from the geometry. In relativity, there is no fixed background that stays untouched. The stage is part of the cast, and it changes with the plot. You can see that dynamical stage in the real universe. Gravitational waves ripple through space-time, stretching and squeezing distances, and detectors like LIGO read those ripples as tiny phase shifts in laser light. Both pillars are spectacularly successful where the other is quiet. Quantum theory dominates atoms, chemistry, and particle physics. Relativity dominates planets, stars, and the expanding universe. The trouble begins when both must speak at once. Black holes, the early universe, and extreme densities demand quantum rules and geometric rules simultaneously. So what does it mean to say physics breaks at the Planck scale? It does not mean experiments have reached a hard wall, although they have. It means our equations start producing answers that cannot be trusted. The breakdown shows up as infinities, contradictions, and loss of predictability. In quantum field theory, calculations often diverge. Renormalization tames many infinities by absorbing them into measured parameters, but gravity resists that treatment. Renormalization works when a theory's high-energy details can be packaged into a few numbers you measure once. For gravity treated as a quantum field, new divergences appear at every order, demanding endless new parameters. When you try to quantize gravity the same way you quantize other forces, the infinities multiply without a consistent cure. The theory stops being predictive at high energies. In general relativity, singularities appear. Curvature becomes infinite, geodesics end, and the theory signals that its own description has run out. The Penrose and Hawking singularity theorem sharpened this discomfort in the 1960s. Under broad conditions, collapse and cosmic expansion lead to incomplete paths, meaning the classical story cannot be continued. A singularity is not just a large number. It is a place where the model cannot say what happens next, even in principle. At the Planck scale, these failures overlap. Quantum theory demands fluctuations of energy in tiny regions. Relativity turns those fluctuations into fluctuating geometry. But standard quantum theory assumes a stable notion of time to define evolution. Standard relativity makes time part of the dynamical geometry that can fluctuate. That is a direct contradiction in the foundations. One framework needs a fixed clock to run the equations. The other says the clock is made of the same uncertain stuff. Even the idea of distance becomes suspect. If spacetime itself is a quantum object, then the ruler is not external to what it measures. What would it mean to compare two lengths if the geometry between them is in superposition? What does here and there mean if the metric itself can fluctuate like a field? return to the opening thought experiment. You try to probe a smaller region with a higher energy particle. Quantum mechanics relates wavelength to momentum. To resolve a length L, you need momentum on the order of Planck's constant divided by L. As L shrinks, the required momentum grows. That momentum corresponds to energy, and energy gravitates. Relativity relates energy in a region to an effective Schwarzschild radius. If the energy is high enough, the radius becomes larger than the region you aimed at. You can think of it as a contest between two scales. One scale is the quantum wavelength you want to shrink, and the other is the gravitational radius that grows as energy concentrates. Then your probe does not reveal substructure. It creates a horizon that blocks the information, and the measurement becomes self-defeating. This is the key tension. The Planck scale is not simply where things are tiny, it is where the operational meaning of measurement collides with gravitational collapse. So the Planck length is not a smallest object in a simple sense. It is a sign that the concept of smaller may stop being well defined. The Planck time is not just a fast tick, it is the scale where the notion of a smooth temporal sequence may dissolve into quantum ambiguity. If spacetime cannot be treated as a smooth manifold at these scales, then our familiar continuum picture is an approximation. The approximation is excellent at large scales, but it may be emergent. Emergent does not mean unreal, it means derived. Temperature is emergent from molecules, and solidity is emergent from electromagnetic forces, so spacetime could also be a large-scale description of deeper degrees of freedom. This is why the stakes are so high. Singularities in black holes and in the Big Bang are not just mathematical curiosities, they are places where our best theories demand answers and then refuse to provide them. They are signposts pointing toward missing physics. If we could describe the Planck regime, we might learn what replaces a singularity. We might learn whether the universe had a beginning, a bounce, or something stranger. We might learn what happens to information that falls into a black hole. We might learn whether horizons are absolute or approximate. We might learn whether spacetime is fundamental or constructed. The Planck scale forces that question because geometry itself becomes uncertain. There are hints, not conclusions. One hint is that spacetime at very small scales may be violently fluctuating, like a foam of transient geometries. In that picture, smooth space is like a calm ocean viewed from far above. Up close, at the Planck length, the surface becomes a storm of peaks and pits, with topology and curvature flickering too quickly for classical language. Another hint is that black holes behave like thermodynamic objects. They have temperature and entropy, which suggests microscopic degrees of freedom we have not identified. Hawking radiation ties quantum fields to horizons, and Beaconstein's entropy ties area to information. The entropy scaling with horizon area, not volume, is a clue that spacetime stores data in an unfamiliar way. Another hint is that quantum entanglement seems to organize geometry in some models. Connections in spacetime may reflect patterns of quantum correlation. Entanglement is a simple word for a precise fact. Quantum states can be linked so that subsystems cannot be described independently. If geometry tracks those links, then distance may partly measure how strongly regions share quantum information. These hints motivate candidate theories. String theory replaces point particles with extended objects, softening interactions at short distances and tying gravity to quantum consistency. Its extra dimensions and vibrational modes are not decorative, they are bookkeeping for consistency. A massless spin-2 excitation appears naturally, behaving like a graviton, as if gravity is demanded by the quantum structure. Loop quantum gravity tries to quantize geometry directly. It predicts discrete spectra for areas and volumes, suggesting spacetime has atomic structure. In that approach, geometry is built from networks of quantized links, and smooth space emerges as a coarse-grained limit. The visual is almost architectural, nodes and edges forming a scaffold that only looks continuous from far away. Other approaches treat spacetime as emergent from quantum information. Geometry becomes a derived concept, built from entanglement, error correction, or collective behavior. The common theme is restraint. Instead of forcing quantum fields onto a fixed stage, they ask whether the stage is itself a collective phenomenon, like a pattern that persists only when many degrees of freedom cooperate. None of these approaches has yet delivered a complete, experimentally confirmed answer. But each is an attempt to resolve the same contradiction at the same boundary. The motif for this story is simple and unsettling. The closer we look, the more spacetime behaves like an object that cannot decide what it is. Sometimes it acts like geometry, smooth and continuous, shaping motion and light. Sometimes it acts like quantum matter, fluctuating, superposed and resistant to definite localization. At ordinary scales, we can ignore the conflict and still predict the world with astonishing accuracy. At the Planck scale, the conflict becomes the main event, so the central question is not only why our equations fail. The deeper question is what the failure is trying to tell us about reality. Is spacetime made of something? Is it a field like others, with quanta and interactions? Or is it a bookkeeping device that emerges from deeper variables? And if measurement itself can trigger horizons, what does it mean to observe the microscopic structure of spacetime? What does it mean to ask a question the universe refuses to answer directly? This chapter sets the boundary and the stakes. The Planck scale is where quantum uncertainty and gravitational collapse collide, and where our two pillars demand a third idea. Next, we follow the breakdown into its most dramatic arenas. We start with singularities and horizons, because they are where the contradiction becomes impossible to ignore. Chapter 1 ended with a boundary that behaves like a reply, almost like an intelligent refusal. Ask for sharper detail, and gravity answers with a horizon, an edge that is not a wall of matter but a limit of information. Now we build that boundary from scratch, using only nature's own ingredients. No meter stick, no clock face, no laboratory convention, and no hidden reliance on earthbound artifacts. The goal is not to measure the wall with human tools, but to show that the wall is implied by the tools themselves. Imagine a rule for the universe's deepest regime, where the familiar categories start to blur. You're allowed only 3 constants, and everything else must be built from them. The speed of light, c, Newton's gravitational constant, g, the reduced Planck constant, h. The question becomes a recipe problem, but the kitchen is the cosmos itself. If those are the only numbers you can use, what length can you possibly construct? What distance is forced on you, even if you never asked for it? This is dimensional analysis as detective work, where units become clues rather than bookkeeping. You do not need the full theory to begin. You track dimensions like fingerprints, and you watch which combinations can exist without contradiction. When the units finally cancel cleanly, you have found a scale that any consistent physics must be able to speak about. Dimensional analysis is not a shortcut around physics, and it does not replace dynamics or mechanisms. It is a way to expose what any consistent physics must respect, even before you know the final equations. It tells you when a proposed story cannot possibly be true, because the units refuse to cooperate. Visually imagine 3 glowing tiles floating in darkness, each marked with a symbol and a set of units. They drift toward one another, rotate and lock together like parts of a machine. The machine does not care who built it, because it is built from invariance. Start with C, because it welds space and time into one structure. It converts seconds into meters, and it sets the maximum speed for signals, influences, and causal chains. In a universe with a finite C, the words before and after cannot be separated from the words here and there. In relativity, C is not just how fast light moves through vacuum, as if light were the main character. It is the conversion factor that makes time behave like a direction, and it fixes the slope of every light cone in spacetime diagrams. Even objects with mass, which never reach C, still live inside the geometry that C defines. If C is finite, causality has a geometry that can be drawn and tested. Events can influence only what lies inside their future light cone, and they can be influenced only by what lies inside their past light cone. Outside those cones, elsewhere, is not merely far away. It is causally disconnected for that moment. This is why C appears in so many places that do not mention light at all. It appears in the energy, mass relation, in time dilation, and in the way momentum and energy fit together. It is a constant that stitches the bookkeeping of the universe into a single ledger. Next is H, the scale of quantum action, and the constant that turns classical certainty into quantum probability. It sets how big quantum effects are when you try to isolate a system, and it determines the granularity of phase space in the simplest operational sense. When H is present, nature does not allow you to specify all properties with unlimited precision. H is the constant behind the uncertainty principle, but the principle is often misheard as a statement about bad instruments. The deeper claim is structural. position and momentum cannot both be made arbitrarily sharp, because the wave-like description is not optional. The mathematics of quantum states forces a trade, and h sets the scale of the trade. In practice, h ties localization to energy cost in a way that becomes brutal at short distances. To confine something to a smaller region, you must accept larger momentum fluctuations, and those fluctuations translate into higher typical energy. The price is not paid in money or engineering, it is paid in the spectrum of the state itself. A useful image is a wave packet being squeezed like a bellows. As the packet narrows in space, it spreads in momentum, and the high momentum components become unavoidable. You can choose the shape of the packet, but you cannot escape the trade that h enforces. Then comes g, the constant that measures how strongly energy curves spacetime, and it is the most deceptive of the three. In everyday units, g is small, which is why gravity looks weak in particle physics, and why we can ignore it in most laboratory calculations. But weakness is not the same as irrelevance, and small constants can dominate when the conditions become extreme. General relativity makes a blunt claim that is easy to say and hard to fully absorb. Anything with energy and momentum contributes to curvature, even radiation and pressure, and even forms of energy that have no rest mass. The source is not mass in the old sense, but the stress-energy content of whatever exists. So C links space and time, H links measurement to irreducible quantum disturbance, and G links energy to the bending of the stage. The three constants do not merely decorate equations, they declare which conceptual separations will survive and which will eventually fail. When you combine them, you are combining the deepest constraints we have found. If you combine these three, you can build units that do not mention humans, planets, or chemical elements. They are not defined by a platinum bar in a vault, and they are not defined by a specific atomic transition that presumes a particular kind of matter. They are defined by the universe's own conversion rates. The logic is simple even when the algebra is not shown, and that is part of its power. Each constant carries dimensions, and only certain products can cancel into a pure length. You search for a combination of C, G, and H that leaves meters behind and cancels everything else, and there is essentially one answer. That answer is the Planck length, and it arrives with an unsettling finality. It is about 1.6 in 16 times 10 to the minus 35 meters, a number so small that ordinary metaphors collapse. If a proton were expanded to the size of the observable universe, the Planck length would still be microscopic by comparison. It helps to anchor that scale with a visual ladder of sizes. A human hair is about 100 micrometers, a cell is a few micrometers, and an atom is about 1/10 of a nanometer. A proton is around a femtometer, and the Planck length is 20 orders of magnitude smaller than that. You can repeat the same reasoning for time, because time and length are tied together by c. Use c to turn length into time, and the Planck time appears as naturally as a shadow following an object. It is the time unit that belongs to the same universal recipe. The Planck time is about 5.39 times 10 to the minus 44 seconds. It is the time light needs to cross one Planck length, which makes it feel like a definition rather than a discovery. Yet that crossing time is also a statement about the fastest meaningful tick a clock could have, if clocks are made of physics. Then you can build a mass scale, and this is where intuition begins to wobble. Combine the same constants and ask for kilograms, not meters, and the result is not the mass of a particle you have ever met. It is a mass that belongs to the junction of two theories. That gives the Planck mass, about 2.18 times 10 to the minus 8 kilograms. It sounds small until you translate it into particle units, where the comparison is not to coins or grains of sand, but to electron masses and proton masses. In that language, the Planck mass is enormous. In particle physics, mass is usually measured as energy, because energy is what experiments directly exchange and conserve. Multiply by c squared, and the Planck mass becomes the Planck energy. Now the number stops sounding modest and starts sounding unreachable. The Planck energy is about 1.22 times 10 to the 19th GeV, far beyond the reach of any collider we can plausibly build. The Large Hadron Collider reaches energies on the order of 10,000 GeV per proton, which is already an engineering triumph. The Planck energy is roughly 15 orders of magnitude higher. This pairing is the first clue to the mystery, and it is a clue with teeth. The Planck energy is enormous, yet the Planck length is unbelievably tiny, and those two facts are not unrelated. They are two sides of the same operational demand. High energy and small distance are not separate ideas in quantum physics, even though we often talk about them as if they were. They are the same demand stated in two languages, because wavelength is a measure of spatial resolution. To see finer detail, you must use shorter wavelengths, and shorter wavelengths require higher momentum. To probe smaller structure, you need shorter wavelengths, and the simplest way to get them is to raise the energy of your probe. Shorter wavelengths require higher momentum, and higher momentum means higher energy, whether the probe is a photon, an electron, or a composite particle. Resolution is purchased with energy, so the Planck length is not just a small ruler mark, and it is not merely a number on a chart. It implies a probe energy so large that gravity cannot stay quiet, because energy is not a passive label. In relativity, energy is a source, and sources reshape the geometry they inhabit. This is where the three constants stop being separate chapters and become one combined constraint. They form a triangle of limits: causality, quantum disturbance, and gravitational back reaction that closes in on the same point. At that point, asking a question changes the stage on which the answer would appear. At ordinary scales, you can treat gravity as a negligible background, and you can ignore G while still getting accurate predictions. That is why quantum electrodynamics can compute magnetic moments to astonishing precision without mentioning spacetime curvature. Gravity is present, but it is too small to matter. At the Planck scale, that habit fails in a dramatic way. The same energy you need to localize a particle becomes a gravitational source strong enough to reshape geometry in the very region you're interrogating. The probe and the target cease to be separable because the probe becomes part of the gravitational environment. You can see the tension without equations by comparing two competing effects that pull in opposite directions. Quantum mechanics punishes localization with momentum uncertainty, which pushes energy upward as you squeeze. General relativity punishes concentrated energy with curvature, which pushes spacetime toward collapse as you concentrate. In GR, the relevant idea is that energy has an effective gravitational radius, which you can picture as a threshold size. If enough energy fits inside that radius, a horizon forms, and the region becomes causally sealed from the outside. The horizon is not a material shell, but a boundary in the light cones. In QM, the relevant idea is that a localized wave packet needs high momentum components, and those components raise the energy you have packed into the region. The uncertainty principle is not merely a blur, it is a demand for energetic support. The sharper the localization, the more violent the momentum content. Push localization harder, and you raise energy, even if your intention is purely observational. Raise energy, and you increase the gravitational radius, because gravity responds to energy itself. The two curves move toward each other, one driven by H and the other driven by G, and C quietly translates between their languages. The Planck scale is where they meet, and the meeting is not gentle. It is where the quantum cost of sharp position becomes the gravitational cost of collapse, and where the act of looking closer risks creating the very horizon that prevents looking. The boundary behaves like a reply because measurement has become an intervention. This is why the Planck units matter, and why they refuse to stay in the footnotes. They are not arbitrary numbers chosen for convenience, and they are not merely a physicist's private system of units. They are the unique scales where C, H, and G all contribute equally, so no single theory can dominate. Max Planck noticed this long before black holes were mainstream physics, and long before quantum field theory took its modern form. In 1899, working in the era when thermodynamics and radiation were pressing mysteries, he saw that C, H, and G define natural units independent of culture. He called them natural because they do not depend on any human choice. At the time, it was a mathematical curiosity, and even Planck treated it as a kind of elegant aside. Later, it became a warning sign because the constants were discovered to govern incompatible frameworks. The same recipe that produces clean units also produces a crossroads where our descriptions collide. Because the Planck length is so tiny, it invites a misunderstanding that is almost irresistible. It is tempting to treat it as the size of a smallest bead, a final pixel of reality, or a hard cutoff in space. But the deeper meaning is operational rather than ontological, and it is about what can be measured without self-defeat. It is the scale where the act of measurement becomes inseparable from the geometry being measured. You cannot treat spacetime as a passive grid while you interrogate it, because the energy required to define the grid points becomes a source of curvature. The ruler bends the table, and the table bends the ruler. The Planck energy makes the same point from the opposite direction, and it does so with a kind of menace. It is the energy required for a probe whose wavelength matches the Planck length, which means it is the energy required to ask for that resolution. That energy is not just large, it is large enough that gravity becomes strong in the region where the probe is focused. In particle physics, strong usually means a large coupling constant, like the strong nuclear force that binds quarks. In gravity, strength also depends on energy scale, because the effective dimensionless measure of gravity grows with energy. Gravity couples to energy itself, so it cannot be screened or cancelled by opposite charges. Gravity couples to energy itself, not to a special charge that can cancel out. If you increase the energy involved, you increase the gravitational effect, and there is no negative gravitational charge to neutralize it. This makes gravity unusual among forces, and it makes high-energy experiments gravitationally dangerous in principle. So gravity is not always weak, even though it is weak in the low-energy world where we evolved. It is weak when the energies and densities are low, and when the spacetime curvature produced is negligible over the region of interest. Change the energy scale and the verdict can change with it. At the Planck scale, the relevant energy density is extreme, and density is the key word. You're trying to place a huge energy into a tiny volume, and gravity responds to density more dramatically than it responds to total mass spread thinly. Concentration is what triggers the crisis. This is the bridge from Chapter 1's hook to this chapter's construction, and it tightens the narrative into a single loop. The wall is built from the same ingredients as the probe, and the probe is built from the same constants as the wall. When you push one, you inevitably push the other. Now connect this to quantum field theory, because QFT is how we actually describe high-energy physics in practice. QFT treats particles as excitations of fields, and fields are defined everywhere, even where no particles are present. The world is not a collection of beads. It is a set of continuous degrees of freedom with quantized excitations. Fields do not sit quietly even in their lowest energy state, and this is one of the most counterintuitive lessons of quantum theory. The vacuum is a restless baseline with fluctuations, a ground state that still contains uncertainty. Even when the average energy is minimized, the field cannot be pinned perfectly to zero everywhere. A vivid way to picture this is to imagine a dark ocean surface under a windless sky. From far away it looks flat, but up close it is always rippling, with tiny peaks and troughs appearing and vanishing. The ripples are not particles in the usual sense, but they are real features of the quantum state. Those fluctuations are usually harmless at macroscopic scales, because they average out when you look at large regions and long times. Their gravitational influence is negligible for most experiments, and we can treat spacetime as effectively rigid. That approximation is so successful that it becomes invisible. But at very short distances, fluctuations become more violent, and the reason is built into the uncertainty principle. The uncertainty principle allows larger energy variations over shorter times, because energy and time are linked through quantum action in a way that sets a trade. The shorter the interval, the less constrained the energy can be. QFT also assumes something crucial, and it is easy to overlook because it is so basic. It assumes a stage on which fields live, with a notion of distance and time already defined, so that you can say what nearby means. Without that background, the field's degrees of freedom cannot even be indexed in the usual way. Even when QFT is placed on curved spacetime, the geometry is typically fixed for the calculation. You calculate quantum behavior on a background you do not quantize, and you treat the metric as given data rather than as an operator with uncertainty. This is not laziness. It is how the theory is constructed. General relativity makes the opposite assumption, and it does so with remarkable consistency. The stage is dynamical, and it responds to whatever energy the fields carry, including the energy of the vacuum and the energy of fluctuations. In GR, geometry is not a container, it is a participant. At low energies, you can pretend these assumptions do not clash, and the pretense works so well that it becomes a standard method. You can do QFT in a nearly flat spacetime, add small curvature corrections, and get predictions that match experiments with astonishing accuracy. The separation holds because the back reaction is tiny. At the Planck scale, the clash becomes unavoidable, and it is not merely a technical inconvenience. Quantum fluctuations in energy imply fluctuations in curvature because G converts energy into geometry. If energy is uncertain, then the curvature sourced by that energy is uncertain as well. If curvature fluctuates, then the metric is uncertain, and the metric is what defines the meaning of distance and time. If the metric is uncertain, then the meaning of distance and time is uncertain, not as a metaphor but as a calculational obstacle. The coordinates lose their operational anchor. That uncertainty is not just philosophical, and it is not a matter of interpretation alone. It threatens the definitions QFT needs to even state its commutators and its time evolution, because those definitions rely on a clean split between space-like and time-like separations. If the light cones jitter, the split becomes ambiguous. In QFT, you define fields at points and relate them across space-like separations, and you rely on locality as a guiding principle. In GR, points and separations are part of the dynamical object, and they can be distorted by the very energy the fields carry. The two frameworks disagree about what is fixed and what is fluctuating. So the Planck scale is not merely where calculations get hard, though they certainly do. It is where the foundational inputs of each theory undermine the other, because each theory assumes what the other makes dynamical. The conflict is built into the starting assumptions. This is the second wall hidden inside the first, and it is more subtle than a horizon. Measurement fails because the geometry becomes part of the quantum system, and the quantum system is what you are trying to measure. The observer cannot stand outside because outside is a geometric concept that is now uncertain. Return to the recipe idea and see why it is so powerful, even as it remains deceptively simple. If you can only build a length from C, G and H, that length is universal, and it is not negotiable. It is not a property of a particular material or a particular technology. It does not depend on the material of your ruler, and it does not depend on the chemistry of your clock. It does not depend on whether you are made of carbon, silicon, or something stranger. It is a scale that any civilization would discover if they learned these constants, because it is a feature of the laws, not of us. That universality is why the Planck scale is a signpost rather than a curiosity. It marks where our current separation of concepts stops being consistent and where a new synthesis is demanded. The signpost does not tell you what the new theory is, but it tells you where the old ones stop agreeing. We separate space from time in everyday life, but C tells us they are linked into spacetime. We separate matter from geometry, but G tells us they are coupled because energy shapes curvature. We separate measurement from disturbance, but H tells us disturbance is built in because states cannot be specified without quantum spread. At the Planck scale, all three separations collapse together, and the collapse is the wall. What does it mean to ask for a position when position depends on a metric, and the metric depends on energy, and the energy depends on the quantum state? The question loops back on itself. This is also why the Planck mass looks strange, and why it is such a useful diagnostic. In kilograms it is tiny, but as an energy it is immense, and the translation between those statements is c squared. The mismatch is not a paradox. It is a reminder that our everyday unit intuition is not built for fundamental scales. The Planck mass is the mass whose Schwarzschild radius is comparable to its Compton wavelength, and that sentence compresses the whole argument. One length comes from gravitational collapse and the other comes from quantum localization. The Planck mass is the balance point where neither length can be ignored. You do not need the formulas to grasp the meaning, but it helps to picture the two lengths as moving targets. The Compton wavelength shrinks as mass grows, because heavier objects are easier to localize quantum mechanically. The Schwarzschild radius grows as mass grows, because heavier objects curve spacetime more strongly. When those lengths match, neither theory can be treated as a correction to the other, and neither can be safely expanded as a small perturbation. They must be solved as one problem, because the regime is defined by their equality. The wall is the demand for a unified description. In the lab, we rarely see gravity and particle interactions, and the numbers make that clear. The gravitational force between two protons is absurdly small compared to their electric repulsion, and it remains small even when the protons are close. That is why particle physics can thrive without general relativity. But the Planck scale is not about two protons sitting apart and politely exchanging forces. It is about concentrating energy into a region so small that its own gravity matters, regardless of what the energy is made of. The key is not the identity of the particles, but the density of energy you create. The Planck energy is the scale where that concentration becomes unavoidable, and where the usual strategy of increase energy to see smaller distances runs into its own consequence. It is the energy at which spacetime responds at the same scale you probe. The microscope starts to distort the specimen by changing the specimen's geometry. This reframes the central question of the documentary, and it makes the mystery feel less like ignorance and more like structure. The breakdown is not a failure of cleverness, and it is not merely a missing term in an equation. It is a clue about what spacetime is, and about whether it can be treated as a smooth continuum. If spacetime were a fixed arena, you could always imagine probing it more finely, because the arena would not react. If spacetime is a quantum object, probing changes the arena itself, and the notion of finer may lose its meaning. The Planck Scale is where that difference stops being academic. It becomes the difference between an answer and an event horizon, between a measurement and a gravitational boundary. It becomes the difference between a question that returns data and a question that returns a new causal structure. The wall is not built to stop you, it is built because the universe must remain self-consistent. So the wall is built from three constants, not from engineering limits, and that is what makes it feel uncanny. It is built from causality, quantum action, and gravitational coupling, and those are not optional features of our world, they are the grammar of physical law. That is why Planck units feel like a boundary rather than a convenience, even though they can be used as a convenient unit system. They tell you when your questions require a theory we do not yet have, because the old theories demand incompatible assumptions. The numbers are not just scales, they are warnings, and they tell you what that missing theory must do, at least in outline, before any details are written down. It must describe quantum systems without assuming a fixed background geometry, because the background must be allowed to fluctuate. It must describe geometry without treating it as a classical field immune to uncertainty, because uncertainty is built in. It must unify the meaning of measurement with the dynamics of space-time, because measurement is how physics connects to reality. If the act of measurement changes the geometry, then measurement must be part of the theory's core, not an afterthought. The wall is a demand for conceptual closure. At this point, the story turns from construction to confrontation, and the camera can begin to move. We have the scale, and we have the logic that forces it upon us, even if we never wanted it. Now we need to see where the conflict becomes visible, and where it becomes impossible to ignore. Next, we follow the breakdown into its most dramatic arenas. We go to horizons and singularities, where the wall stops being abstract, and where the universe demonstrates, without apology, what it does to questions that ask for too much. Chapter 1 promised a boundary where sharper questions stop producing sharper answers, and it hinted that the boundary would feel less like a wall than a snare. Chapter 2 built that boundary from C, H, and G, and it showed why those constants make the limit universal. Now we step into the mechanism that makes the boundary feel like a trap. On screen, imagine a clean laboratory dissolving into abstraction. Rulers fade, grid lines warp, and the simple act of looking closer becomes a physical event. Stainless steel benches soften into fog, and the crisp tick marks of instruments stretch like rubber as the camera pushes inward. At human scales, measurement feels like reading a dial, or counting ticks on a clock, or lining up marks on a ruler. We treat the world as though it sits there, patiently waiting to be sampled, while our tools remain politely external. At very small scales, measurement is not passive, and it is not merely observational, because the system cannot be cleanly separated from the act of interrogation. To learn where something is, you must interact with it, and the interaction is the experiment. The probe is not an accessory to the story, it is a character that barges into the plot. At ordinary scales, the disturbance can be engineered into near invisibility, because the probe's influence is tiny compared to the system's inertia and environment. A flashlight does not shove a basketball across the floor, and a camera does not collapse a building by photographing it. Even a thermometer, which exchanges energy by design, can be made gentle enough that it barely perturbs what it reads. But at extreme scales, the disturbance becomes the main physical effect, and the measurement apparatus becomes part of the phenomenon. The question is no longer, what is there, but what does it mean to ask? When the asking changes the stage on which the answer would appear. Physics survives by operational definitions, definitions tied to procedures that can, at least in principle, be carried out. When those procedures self-destruct, the definition goes with them. Start with the simplest operational goal, because operational meaning is the only meaning that survives in physics. Define a distance dx by localizing a particle inside that region so that inside and outside become physically distinguishable. If you can localize it, you can claim the region has meaning, because some procedure can pick it out. If you cannot localize anything, the notion of that distance becomes empty, like a coordinate drawn on a map with no way to navigate. This is why the story begins with a particle, not with a philosophical debate about space. In practice, we define lengths by interactions, scattering, absorption, emission, or timing signals that bounce and return. Even the most refined metrology is still a choreography of exchanges, and at small scales the choreography becomes violent. The distance is not a number you read off reality. It is a number you extract by forcing reality to respond. Quantum mechanics gives a blunt trade, and it is not optional. The more tightly you confine position, the less certain momentum becomes, because the state must contain a wider range of momenta to build a narrower spatial profile. In plain terms, squeezing a wave packet forces in shorter waves, and those shorter waves are the ones that can fit inside a tight region. Shorter waves carry larger momentum components, and you cannot remove them without undoing the localization. Visually think of a calm ocean surface becoming a choppy, high-frequency ripple as you demand a sharper edge. Smooth swells replaced by tight corrugations that refuse to sit still. The wave packet is not a little bead with a fuzzy outline, but a superposition whose shape is built from many wavelengths. When you demand a small dx, you demand a broad spectrum, and the spectrum is momentum. This is not a limitation of instruments, because it is a property of the quantum state itself. Heisenberg uncertainty is often taught as a limit on knowledge, as though the particle has a definite position and momentum, but refuses to tell you both. Here it is a limit on procedure, which is a more physical statement, because it binds what you can prepare and what you can extract. If you demand dx, you must accept a momentum spread roughly h divided by dx, because that spread is what makes the localization possible. The act of localization builds high momentum into the state, whether you like it or not. Historically, this idea arrived as a shock, because classical physics trained intuition to separate what is from how you look. In the 19th century, measurement was idealized as a kind of gentle bookkeeping, with errors treated as imperfections rather than consequences. By the 1920s, that comfort collapsed, and the collapse was not aesthetic, it was forced by experiments. The microscope became a symbol for this shift, because it is a concrete device with a concrete limitation. Heisenberg's gamma-ray microscope thought experiment was not a gadget proposal, but a warning. To see finer detail, you must use shorter wavelengths, and shorter wavelengths carry more momentum. In the story's visual language, the microscope's lens becomes a funnel for energy, narrowing the beam until it behaves less like illumination and more like impact. The microscope in quantum theory is never just a window. To actually measure dx, you need a probe that can resolve that scale, and resolution means wavelength. A probe with wavelength much larger than dx cannot distinguish features inside dx, because the wave does not fit into the region with enough phase variation to encode detail. Diffraction and wave interference smear the information, turning sharp boundaries into blurred patterns. Even before quantum enters, wave optics already tells you that there is a price for focus. On screen, a beam narrows through a lens, but the focal spot refuses to become a mathematical point. Rings and halos appear, the airy disk that every optical engineer learns to respect. The image shimmers with concentric structure, and the narrator can linger on the stubbornness of those rings. That pattern is not a defect in glass, but a signature of wave propagation. A wave that is forced through an aperture spreads, and a wave that tries to localize must carry the spatial frequencies that localization demands. The same logic extends far beyond visible light, because it is not about eyes or cameras, but about Fourier structure. If you want to carve a boundary in space, you need high spatial frequencies, and high spatial frequencies correspond to large momenta. The mathematics is compact, but the meaning is plain. Sharpness costs. So you choose a probe with wavelength comparable to dx, because anything longer is too blunt to carve out the region. For photons, wavelength and momentum are inversely linked, and the relationship is exact enough to be ruthless. Shorter wavelength means larger momentum, and larger momentum means larger energy, because for a photon energy is PC. The probe becomes not just more precise, but more intense in its physical impact. This is the microscope rule that never goes away, even when the microscope is no longer made of glass. Zooming in is inherently energetic because resolution is not a software trick, but a physical constraint. It is not a preference for engineers, and it is not a limitation of current materials. It is a consequence of wave behavior and quantum kinematics, written into the structure of the theory. Translate that into a concrete step because the trap is easiest to see when you do the bookkeeping. You send in a photon with wavelength L about dx, and you aim to scatter it off the target so that the scattering tells you where the target is. Its energy is about hc divided by L, and its momentum is about h divided by L. As L shrinks, energy rises, and the probe becomes a concentrated packet of energy aimed at a tiny region. Picture the probe as a flash that is not merely bright, but compressed into a microscopic volume for a microscopic time. Like lightning forced through a needle's eye, the smaller the region you demand, the more the flash resembles a hammer strike rather than a gentle touch. In quantum field language, you're injecting high-frequency modes, and those modes carry stress energy. The act of asking where becomes an act of delivering energy. At first, this is exactly how physics progresses, and it is worth remembering how successful this strategy has been. Higher energy scattering reveals smaller structure because momentum transfer sets the scale of what you can resolve. You infer size from angles, recoil, and momentum exchange, and you build a map from statistics, not from direct pictures. Particle physics is a discipline of indirect vision, where the image is reconstructed from tracks and counts. Historically, this approach turned atoms from speculation into measurement, and it turned nuclei from mystery into geometry. Rutherford's scattering experiments used energetic alpha particles to reveal a tiny dense nucleus, because large deflections implied a concentrated charge. Later, deep inelastic scattering at SLEC revealed that protons behave as though they contain point-like constituents, because high momentum transfer exposed substructure. The method is clear: to see smaller, hit harder. But gravity does not stay silent when energy density becomes extreme, and this is where the familiar method begins to betray itself. General relativity treats energy and momentum as sources of curvature, and it does not care whether the energy is rest mass or radiation. It cares about what stress energy you concentrate, including pressure and flux, because those also gravitate. In Einstein's theory, energy is not just something you carry, it is something that shapes the stage. On screen, the clean grid of spacetime becomes elastic, then heavy, then unstable, as though the probe itself presses a dent into reality. The grid does not merely bend under the target, it bends under the question you asked. This is not metaphor in the equations, because curvature is encoded in the metric, and the metric determines what distance even means. The probe is not merely interacting with the particle, it is interacting with geometry. The measurement becomes self-referential, because you're using a notion of distance to define the very act that changes distance. When the metric shifts, the meaning of your coordinate label shifts with it, like trying to measure a rubber sheet while your ruler stretches the sheet. The experiment's background assumptions become moving parts. To see the collision of principles, introduce the gravitational length scale tied to energy, because gravity has its own way of converting how much into how big. For a mass m, the Schwarzschild radius is about 2 gm divided by c squared, and it marks where an event horizon would form for a non-rotating, uncharged black hole. For energy E, you use mass equivalence, because E over c squared plays the role of m. The conversion is not philosophical, it is a bookkeeping identity that gravity respects. That gives a gravitational radius tied directly to the probe energy, and the direction of the trend is the key. The more energy you pack into the interaction region, the larger the associated Schwarzschild radius becomes, because gravity responds to the total energy content. This is the opposite trend from quantum resolution, which demands smaller L and therefore higher energy. Quantum asks you to shrink the probe's wavelength, and gravity answers by swelling the radius of collapse. Now put the two demands on the same axis, and let the viewer feel the squeeze. You try to make dx smaller, because you want a sharper operational definition of distance. Quantum mechanics forces the probe energy upward, roughly E about hc divided by dx, because wavelength and resolution are linked. General relativity turns that energy into a Schwarzschild radius, roughly Rs about ge divided by c to the fourth, up to factors of order 1. The two curves move in opposite directions. As dx shrinks, E rises, and as E rises, Rs grows, and the growth is not gentle. Eventually Rs is no longer negligible compared to dx, and the probe's own gravitational influence becomes part of the experiment's geometry. At that point, the interaction region becomes its own gravitational trap, and the measurement apparatus begins to manufacture the very boundary that blocks the measurement. The microscope becomes a source of horizons. This is the measurement paradox in one sentence, and it is sharper than it first appears. The better your resolution, the stronger your gravitational back reaction becomes. Because energy density is the currency of both precision and curvature, the probe stops being a gentle question and becomes a source that reshapes the answer space. You are not merely reading a property, you are changing the causal structure that defines what properties can be read. Imagine the moment of failure operationally, because the trap is not abstract when you picture it as a sequence of steps. You focus enough energy into a region you intend to interrogate, and you wait for the scattered signal to return. The geometry responds by forming an event horizon around that region, and the horizon is not a wall but a change in what paths are possible. Like cones tip inward, and future-directed trajectories that once escaped now fall deeper. On screen, rays that used to fan outward begin to bend, then curl, then vanish into a darkened center. The visual is not a fantasy effect, because null geodesics are the paths light follows, and curvature changes those paths. The escape routes for information are not blocked by a material barrier, but by the structure of spacetime itself. The experiment has created a one-way membrane for causality. An event horizon is not a material shell, and it is not located by a local sensor that beeps when you cross it. It is a causal boundary defined globally, meaning it depends on the entire future of spacetime, which already hints at why it is so conceptually strange. Once it forms, the outside observer cannot retrieve detailed information about what happened inside beyond a few global charges. The measurement returns less information than the setup demanded. This is where black hole no-hair language becomes relevant, because it captures the course outcome in a memorable way. From far away, a black hole is described by mass, charge, and spin, and many microscopic details are hidden behind the horizon. The outside description becomes brutally compressed, as though nature has applied a lossy algorithm to the state. In the measurement trap, your experiment is pushed toward that same course summary. The trap is that the horizon forms from the measurement itself, and that twist is what makes the Planck boundary feel inevitable. You do not need an astrophysical black hole, and you do not need a dying star or a galactic center. You create a tiny one by concentrating energy, because gravity couples to energy with no regard for your intentions. The act of asking the question changes the causal structure that defines what an answer can be. This is why the Planck Scale is not just a small number at the bottom of a chart, and not merely a badge of theoretical sophistication. It is the crossover where the quantum wavelength you need and the gravitational radius you create become comparable, so the two theories stop taking turns and start interfering. Below that, the operational definition of distance becomes self-defeating, because the procedure that defines the distance also destroys access to it. You can see the balance without heavy algebra, and that simplicity is part of the argument's force. Set the localization scale dx equal to the Schwarzschild radius associated with the required energy, because the breakdown occurs when the horizon is as large as the region. Quantum says E grows like 1 over dx, and gravity says Rs grows like E, so the product becomes constant. Combine them and you get a minimum dx tied to hgc3, which is the only length you can build from those constants. That minimum is the Planck length, up to factors of order 1, and it is astonishingly small, so small that ordinary metaphors fail before the number does. It is not a smallest object by decree, and it is not a claim that space is made of little bricks. It is a smallest resolvable distance by any procedure that uses quantum probes and respects gravitational collapse. The limit is built into the combined logic, as though the universe has placed a regulator on its own description. The conclusion is harsh, and it is meant to be. Try to probe below roughly the Planck length and you do not reveal finer structure, because the probe's energy does not behave like a harmless spotlight. You trigger collapse into a micro black hole, and the target and probe become hidden behind an event horizon that you created. The experiment becomes a device for producing ignorance, not knowledge. It helps to linger on what micro black hole means here, because the phrase can sound like science fiction. The point is not that a stable, long-lived black hole sits in your lab like a marble of darkness. The point is that the gravitational radius associated with the energy becomes comparable to the region, so classical notions of inside and outside are replaced by horizon logic. Even if the object is fleeting, the causal obstruction is the key. A fleeting horizon is still a horizon in the only sense that matters for measurement. Signals that would have escaped are delayed, redshifted, or trapped. The outside world receives a distorted echo, not the crisp return you designed your apparatus to collect. The sharper the intended snapshot, the more the shutter becomes a gravitational choke point. This is not a statement about current technology, and it is not a pessimistic comment about budgets or engineering. It is not about building a bigger accelerator or a better detector, because the scaling argument does not care how clever you are. Any device that tries to localize energy into a smaller region faces the same trade, because wavelength and energy are linked, and energy and curvature are linked. The limitation is conceptual because it is about what measurement can mean. Even if you imagine perfect mirrors and perfect focusing, the energy requirement remains, because the requirement comes from Fourier structure and quantum commutators, not from glass imperfections. Even if you imagine a probe that is not a photon, the de Broglie relation still ties wavelength to momentum, and momentum implies energy. You can swap the messenger, but you cannot escape the logic of localization. The only way out would be new physics that changes the rules of localization or gravity. At this point, a thought-provoking question becomes unavoidable, and it is the kind that reshapes how you interpret every later chapter. If distance is defined by what can be operationally resolved, and if operational resolution collapses into horizons, then what is distance below the boundary? Is it a property that exists but is inaccessible, or is it a concept that loses meaning because no procedure can anchor it? The trap forces you to confront the difference between reality and description. The trap also reframes what we mean by information, because measurement is ultimately an information-gathering act. In ordinary experiments, more energy can mean more data, because you overcome noise and probe finer structure. Here, more energy can mean less accessible data, because horizons erase details from the outside description. Precision becomes censorship, and the word censorship is not just poetic, because it describes a causal restriction on what can be transmitted. This censorship has a familiar echo in black hole physics, and the echo is not accidental. From far away, a black hole is described by mass, charge, and spin, and the messy details of what formed it are not directly observable. The measurement process pushes your experiment toward that same coarse description, as though the universe insists on summarizing what you tried to specify. Your attempt at fine-grained localization produces a system whose external observables are few. On screen, the experiment's readout becomes simplified, as though a rich waveform collapses into 3 numbers. The detector still registers something, but the something is not the detailed map you aim to draw. It is a silhouette, a gravitational signature, a minimal label. The more you try to sharpen the picture, the more the picture becomes a shadow. So the Planck boundary behaves like a protective rule, even if it is not designed with intent. Push too hard on localization, and the universe responds by denying you the degrees of freedom you try to isolate. It answers with darkness, not because it is hostile, but because causal structure has changed. The darkness is not an absence of events, but an absence of accessible paths. At this point, the central question sharpens, and it is worth stating it with care. Why do quantum mechanics and general relativity fail together at this scale, instead of one smoothly absorbing the other? They fail because each assumes a clean separation that measurement destroys, and the thought experiment exposes that assumption. Quantum theory assumes a background notion of distance, even when it treats fields and particles probabilistically. Relativity makes distance dynamical and sensitive to energy, even when the energy is your probe. There is also a subtle asymmetry that makes the conflict feel like a trap rather than a mere mismatch. In quantum mechanics, the probe's disturbance is part of the state you prepare, and you can often account for it and subtract it statistically. In general relativity, the probe's energy changes the geometry that defines the measurement's meaning, and that change cannot be treated as a small correction once horizons appear. The disturbance is not an error bar, it is a new spacetime. The measurement trap shows that the conflict is not limited to exotic objects, and it is not confined to the interior of astrophysical black holes. It appears in a simple thought experiment about defining distance, which is the most basic ingredient of any theory with geometry. The breakdown is not only in equations, although the equations certainly strain. It is in the operational meaning of the concepts the equations use, which is a deeper kind of failure. This is why the Planck scale has such narrative power in theoretical physics. Even though it is far beyond direct experiment, It is the scale where the ordinary ladder of inference, probe, scatter, reconstruct, begins to eat its own rungs. The trap is not a technical obstacle that patient engineering will overcome, but a structural feature of how measurement works when gravity is included. The closer you look, the more you change what closer means. The paradox also suggests a new picture of the vacuum, and the suggestion is not arbitrary. If concentrated energy can nucleate horizons, then violent fluctuations might do something similar, even if only for an instant. At Planck scales, the vacuum is not just fluctuating fields on a calm stage, because the stage itself is sensitive to energy. The stage itself may fluctuate into transient geometries, as though space-time has its own quantum jitter. On screen, empty space is no longer empty, but a restless texture. Brief dimples, sudden pinches, momentary tunnels that do not last long enough to be navigated. The visuals should feel unstable, but not chaotic for its own sake, because the instability is driven by a clear idea. Quantum uncertainty allows energy fluctuations, and gravity turns energy into curvature, so the vacuum becomes a feedback loop. The question becomes whether the loop is tame or wild. This is the doorway to spacetime foam, a phrase that carries both imagery and caution. The idea is not that space is literally filled with tiny permanent holes, like Swiss cheese frozen in place. The idea is that at very short scales, geometry may be a restless quantum object, with curvature and perhaps topology, flickering as uncertainty and gravity feed back on each other. The foam is a metaphor for a regime where smoothness is an approximation. Spacetime foam is a hypothesis, not a settled fact, and that distinction matters because the boundary is conceptual, not yet empirical. But it is a natural continuation of the measurement trap, because the trap tells you that energy localization creates gravitational structure. If measurement energy can create horizons, then quantum fluctuations of energy might create horizon-like structures briefly, and those structures would scramble the notion of a fixed neighborhood. The vacuum could become a storm of causal boundaries. That storm would change what locality means, and locality is the quiet assumption behind almost every calculation in physics. If horizons and strong curvature appear and disappear, the notion of a fixed neighborhood breaks down because nearby depends on the metric, and the metric is fluctuating. The idea of a point becomes suspect, because a point is defined by arbitrarily small neighborhoods, and the trap denies arbitrarily small neighborhoods operational meaning. The continuum becomes an approximation that works only when fluctuations average out. This is where the mysterious tone becomes earned, because the argument has not relied on mysticism, only on two successful theories pushed into the same corner. The Planck scale is not just far away on a chart, and it is not merely a frontier for specialists. It is a regime where the universe may prevent direct inspection by turning probes into gravitational objects, and where the act of measurement threatens to create the very darkness it tries to penetrate. The closer you look, the less the notion of looking applies. Hold the tension on a single beat, because the cadence of the trap matters for what follows. The universe enforces a censorship, and the censorship is causal rather than moral. Demand more precision, and it answers with an event horizon, which is a boundary in what can influence what. The measurement becomes a black hole, and the black hole becomes the measurement, collapsing the distinction between instrument and object. It is worth pausing on a final, unsettling observation, because it reframes the ambition of ultimate resolution. In ordinary science, we assume that if we could build a sufficiently refined instrument, nature would yield finer detail. Here, the instrument's refinement is what produces the obstruction, because refinement requires energy concentration, and energy concentration gravitates. The trap suggests that the universe does not merely hide answers behind complexity, but behind the structure of causality itself. This is the hinge for what comes next, and it follows directly from the logic we have built. If horizons can appear from concentrated energy, then horizons are not rare astrophysical accidents, and they are not confined to collapsed stars. They are a generic feature of gravity plus quantum localization, which means they belong to the foundations, not the exceptions. The Planck scale becomes a laboratory of principles, not a place. Next, we follow this logic into the arenas where horizons and information are already central. We move from the measurement trap to the deeper problem of what horizons do to quantum states, and we ask what becomes of information when the boundary is not a metaphor. We ask what survives when geometry itself becomes uncertain, and when the observer cannot be cleanly separated from the observed. We end this chapter with a controlled contradiction. because the contradiction is the engine of the story. To define smaller distances, you must use higher energy, and the link between wavelength and energy makes that unavoidable. Higher energy curves space-time more strongly, because gravity couples to stress energy with no exemptions. Strong curvature can hide the region behind a horizon, and the horizon blocks the very signals you hoped would return. The attempt to see more becomes the mechanism that guarantees you see less, and that is the trap in its final form. That is why physics breaks at the Planck Scale, not as a failure of imagination but as a collision of principles. It is the boundary where measurement, geometry, and quantum uncertainty become the same problem. Whatever replaces our current theories must tell us how information and spacetime coexist, when every sharper question risks creating darkness. General relativity begins with a quiet promise, almost a gentleman's agreement between mathematics and the physical world. Spacetime is smooth enough to differentiate, and curvature changes gently from point to point, so you can define vectors, transport them, and still trust the idea of a local neighbourhood. In practice, that means you can draw a coordinate grid, take derivatives, and trust that nearby points behave like nearby points. The manifold is assumed to be well behaved under magnification, and the metric is assumed to be a stable object you can consult like a calibrated instrument. On screen, this promise looks like a calm fabric. A faint lattice stretches into the distance, and massive objects press it down in broad, predictable wells that taper smoothly outward. The curves are continuous, the lines are clean, and the geometry feels like something you could measure with a ruler. Even the language of the theory reinforces that calm. We talk about geodesics, smooth trajectories that extremize proper time, and we imagine clocks and light rays tracing elegant arcs through a gently curved arena. The mathematics implies a world where the notion of here can be refined without changing what here means. Quantum mechanics begins with a different promise, and it is less soothing. Even empty space is restless, and uncertainty never allows perfect stillness, not for position, not for momentum, and not for fields. The vacuum is not a featureless void, but a state with irreducible fluctuations that cannot be turned off. Visually, the calm grid is replaced by a shimmer. The background seems to sparkle with transient patterns, brief ripples that appear and vanish before the eye can settle, like heat haze above asphalt, except the haze is the ground itself. Nothing is stable enough to be perfectly still, not even the ground state. In the everyday world, those promises rarely collide, and that is part of why modern physics feels so successful. Gravity is weak at particle scales, so quantum fields can fluctuate on an almost fixed stage and the stage barely notices. In a laboratory, the metric is effectively flat, and the quantum drama plays out without bending the theatre. That separation is an approximation, not a principle, and approximations always come with a price. It works because typical energies are low, and curvature sourced by vacuum noise averages away when you coarse grain over many fluctuations. Over macroscopic distances, positive and negative contributions tend to cancel, leaving a smooth, effective geometry. The cancellation is also statistical, not magical. Quantum fluctuations have correlations, but they're usually short-ranged in the sense that their net gravitational imprint washes out when you do not insist on microscopic resolution. The world looks classical because we are, in effect, looking with a wide lens. But Chapter 3 showed the trap, and it was not merely philosophical. Push resolution far enough, and energy density becomes geometry, threatening horizons and operational meaning in the same motion. The act of probing, when taken to extremes, begins to build the very gravitational structure that blocks the probe. Now we turn from the probe to the vacuum itself. The question becomes what spacetime looks like when the vacuum is the source, not a passive backdrop. If the vacuum is never truly quiet, then what happens when its restlessness is allowed to gravitate? In quantum field theory, fields do not vanish in the vacuum, even when no particles are present. They occupy a ground state with unavoidable fluctuations around their mean values, and those fluctuations are not optional decoration. The field's value and its conjugate momentum cannot both be sharp, so the vacuum carries a baseline jitter. This is not just a metaphor for ignorance, and it is not a statement about imperfect instruments. It is a statement about operators and commutators, written into the algebra of the theory, and enforced by the structure of Hilbert space. The vacuum is the lowest energy state, yet it still contains correlations that extend across space and time. Those correlations have a distinctive character. Even when the expectation value of a field is 0, the expectation value of its square is not, which means the vacuum has variance, and variance is physical. In plain language, the vacuum is calm only on average, while it is busy in detail. Those fluctuations are not optional bookkeeping, and they are not a trick of notation. They are enforced by commutators, and they show up in measurable effects like the Casimir force, which turns a nothing into a pressure. Two uncharged plates placed close together feel an attraction, because the allowed vacuum modes between them are restricted. The visual can linger on that experiment for a moment. Two metallic plates hang in a clean chamber, and as they approach, an invisible squeeze seems to build between them. The narrator can almost hear the silence becoming structured. Empty space, when constrained, pushes back. A useful shorthand is energy-time uncertainty, although the phrase can mislead if taken too literally. Over short times, the vacuum can borrow energy in transient spikes, then return it, but the bookkeeping is subtle. The key idea is that short-lived excitations can exist without violating the overall conservation laws. In a visual sequence, the vacuum becomes a sea of flickers. Peaks rise and fall like whitecaps on dark water, each crest collapsing before it can become a lasting object, and the camera never quite finds a stable frame. The scene suggests motion without a moving medium, activity without a classical source. In ordinary particle physics, those spikes are treated as internal lines. Virtual excitations appear in loop diagrams, then cancel into finite predictions, and the cancellations are guided by symmetry and careful regularization. They contribute to scattering amplitudes, shift masses and charges, and subtly modify forces, yet they do not appear as free particles. That cancellation assumes the background is stable, and stability here means more than calmness. The vacuum fluctuates, but the metric used to define distance and time remains classical, so the rules of momentum and energy are well defined. The stage may be quiet or noisy, yet the stage itself does not wobble. General relativity refuses that split, because it ties geometry to whatever carries energy and momentum. Stress energy curves space-time, and it includes pressures, fluxes, and whatever energy the vacuum effectively carries, even if that energy is hard to define locally. In Einstein's equations, energy density is not privileged over pressure, and both shape curvature. This is where a familiar constant quietly enters the story. Einstein's equations allow a cosmological constant, a uniform energy density of the vacuum that acts like a built-in curvature scale. Historically, it was introduced, abandoned, and later reinterpreted, an early hint that empty space can still weigh something. So the key change at the Planck scale is not louder matter noise. The key change is that the noise becomes geometric, and geometry stops being a silent referee. The vacuum's fluctuations stop being mere actors on a fixed stage, and begin to tug at the stage's beams. If energy fluctuates, curvature fluctuates, and the connection is direct. If curvature fluctuates, the metric fluctuates, and the idea of a single fixed geometry fails in the way a single shoreline fails during a storm. The object we use to define intervals becomes part of the quantum uncertainty. Distance is defined by the metric, and that definition is usually taken for granted. When the metric becomes uncertain, distance becomes a quantum variable, not a clean input, and it can no longer be treated as an exact parameter. Even the statement, "these two events are separated by this much," becomes probabilistic. Causality is also defined by the metric, and this is where the stakes rise. Light cones depend on geometry, so fluctuating curvature means fluctuating causal structure, not just fluctuating measurements. The boundary between what can influence what is no longer a rigid universal shape. The visuals can make this concrete. Light cones appear as translucent cones in space, then they wobble, narrow, and flare as the background geometry jitters. The cones overlap in strange ways. Causal order, which felt absolute, begins to look negotiable. This is where the documentary's central question sharpens into something almost uncomfortable. Quantum theory needs a stable notion of time evolution, but gravity makes time part of the state, not an external metronome. If time is not a fixed external parameter, then what does it mean to evolve a quantum system? At low energies, we hide the conflict by doing quantum field theory on curved backgrounds. We quantize matter fields, then treat the geometry as a given classical solution, and we compute expectation values on that fixed stage. This semi-classical approach is powerful, and it has explained particle creation in expanding universes and near horizons. Historically, This was one of the great conceptual bridges of the 20th century. It connected Einstein's geometry to the quantum vacuum, and it revealed that no particle is not an invariant statement when spacetime itself changes. The vacuum depends on the observer, and the observer depends on the geometry. In visuals, we see a classical spacetime, perhaps a black hole or an expanding cosmos, overlaid with quantum ripples. The geometry is drawn as a smooth surface, while the fields appear as translucent waves moving across it, like a faint aurora sliding over a globe. The two layers interact, but only one is allowed to be truly quantum. At Planck energies, back reaction is not a correction. The vacuum fluctuations that quantum field theory predicts become strong enough to reshape the stage, and the stage can no longer be treated as an unchanging reference. The approximation that geometry is fixed begins to fail, not by a small amount, but by a structural collapse. The Planck scale is not just a number, and it is not chosen arbitrarily. It is built from the constants that define quantum theory, relativity and gravity, h, c and g, combined in the only way that yields a length. Combine them, and you get a length around 10⁻35 meters and a time around 10⁻44 seconds, scales where our usual units feel almost meaningless. These scales are not merely tiny, they are conceptually loaded. They mark where quantum fluctuations of energy, when packed into a region, produce curvature comparable to the region's own size. The constants conspire to say that beyond this point, the continuum picture stops being a safe assumption. John Wheeler gave this regime a name, and the name is deliberately evocative. Spacetime foam is the idea that geometry itself becomes a froth of quantum fluctuations, a restless microstructure beneath the smooth surface. Wheeler was not describing a decorative texture, but a warning about what happens when you push the continuum too far. There is also a historical mood behind the term. Wheeler worked in an era when quantum electrodynamics had shown how vacuum fluctuations could be tamed and measured, and he wondered what the vacuum would do to gravity in return. The phrase foam was a way to make an abstract instability feel tangible. Foam is not a claim that space is literally made of bubbles. It is a warning that smoothness is emergent, and the continuum is an approximation that may fail under sufficient magnification. What looks like a calm surface from far away may be jagged and unstable when magnified enough. In the foam picture, curvature fluctuates violently at tiny scales, as if space-time cannot decide on a shape. Even topology may fluctuate, so the connectivity of space is not fixed, and the notion of a single global chart becomes unreliable. The question, is this region connected to that one, becomes a quantum question, not a settled fact. Topology change is especially unsettling because it is not just a change in curvature. A curved surface is still the same surface, but topology change is a change in what counts as a continuous path. It suggests that the vacuum might briefly allow tunnels, handles, or pinches, then erase them before any classical observer can map them. A manifold assumes you can zoom in forever and still find a well-defined neighborhood. Foam suggests that the zoom reveals instability, not sharper points, and it undermines the idea that coordinates can be refined without consequence. The closer you look, the less the concept of a point behaves like a point. On screen, the camera dives toward a smooth grid, and the grid begins to tremble. Lines that were straight become kinked, then break into swirling fragments, as if the lattice were made of smoke rather than wire. Tiny tunnels appear like momentary shortcuts, then pinch off before they can be traced. The sound design can echo the idea. A low, steady tone accompanies the smooth grid, then it fractures into granular clicks as the scale shrinks. The viewer feels, even without equations, that the notion of a stable background is dissolving. The opening hook returns in a new form, and it now sounds like a challenge. Ask for more precision, and the vacuum may answer back with gravitational structure, not with a clearer picture. The very act of defining a sharper location may summon curvature that destroys the definition. One consequence is the idea of virtual black holes, a phrase that sounds like science fiction but arises from sober dimensional reasoning. If energy spikes concentrate within a small region, their gravitational radius can briefly compete with the region's size. When the Schwarzschild radius associated with that energy becomes comparable to the region's size, horizons are no longer exotic. The Schwarzschild radius is usually introduced with stars and collapse, but the formula itself is indifferent to origin. It only cares about energy and concentration, and at the Planck scale the bookkeeping becomes unforgiving. A fluctuation that would be harmless in electromagnetism can become geometrically decisive in gravity. These are not astrophysical objects with long lives, and they are not formed by collapsing stars. They are fleeting horizon-like configurations, appearing as quantum fluctuations of geometry, and they vanish as quickly as they appear. The horizon is not a permanent boundary, but a temporary feature in a rapidly changing metric. Visually, we might see tiny dark spheres blink into existence inside the shimmering vacuum. Each one casts a brief shadow on the grid, then evaporates into the same restless background, leaving no classical remnant. The effect is unsettling because it makes empty space look crowded with transient boundaries. If such horizons flicker, locality becomes fragile, and fragility here is conceptual. A local interaction assumes a stable notion of nearby, but nearby depends on the metric, and the metric is now part of the quantum state. If the metric jitters, then nearby is not a fixed relation. Quantum field theory encodes locality through commutators, and the rule is crisp. Fields at space-like separation commute, enforcing that signals do not travel faster than light, and this condition is built into the architecture of relativistic quantum theory. It is one of the deep reasons the theory avoids causal paradoxes, but space-like separation is defined by the light cone, and the light cone is defined by geometry. If the light cone jitters, the separation classification becomes ambiguous, and the algebra loses its clean domain of application. Two events might be space-like in one microscopic geometry and time-like in another, within the same quantum superposition. That ambiguity is not merely semantic. The meaning of independent degrees of freedom depends on causal separation, and causal separation depends on the metric. If the metric is uncertain, then independence becomes scale-dependent, and the usual factorization of systems becomes suspect. So the foam threatens more than measurement, and it threatens more than technical convenience. It threatens the logical scaffolding of local quantum field theory, including how we define causality and how we define a system. The very distinction between cause and effect can blur when the causal structure is not fixed. This is also where before and after begin to blur, and the language becomes strained. Time ordering assumes a stable causal structure, but fluctuating geometry scrambles the ordering, and it scrambles it in a way no classical clock can track. If there is no single light cone, then there is no single global answer to which came first. A thought lingers here, and it is worth letting it hang in the air. If the vacuum can rearrange the causal order of microscopic events, what becomes of the idea of a universal clock that ticks for everything? Is time a background, or is it a collective behavior that only appears when fluctuations average out? The visuals can slow down and breathe. A sequence of events is shown as dots connected by arrows, then the arrows fade and reappear in different directions as the geometry flickers. The viewer is left with an uneasy impression. History itself may be a macroscopic approximation. None of this is claimed as a final picture, and that restraint matters. It is a diagnosis of what our current frameworks imply when pushed to their shared boundary, and it is meant to be taken as a warning label. The foam is a signpost, not a completed map. To see the diagnosis in equations, physicists tried the most direct move, and the move was historically natural. Treat gravity like other forces, and quantize small ripples of the metric, using the same perturbative logic that worked elsewhere. If electromagnetism has photons, then perhaps gravity has gravitons, and perhaps the same machinery will work. In that approach, the graviton plays the role of the photon, at least at first glance. You expand around a background metric, then compute interactions perturbatively, and you interpret the small deviations as a quantum field. The background might be flat Minkowski space, and the ripple becomes a quantum field with spin 2. The spin matters because it encodes how the field transforms, and gravity's spin 2 nature is not a detail. It is tied to the equivalence principle, and it forces gravity to couple universally to energy and momentum. That universality is beautiful at low energies, but it becomes dangerous in the ultraviolet. Visually, we see a smooth surface again, but now it trembles with tiny waves. Each wave is labelled as a graviton mode, and interaction vertices appear as clean junctions, like a textbook diagram hovering in space. The diagram language feels familiar, almost comforting, because it resembles the successful playbook of particle physics. The trouble appears immediately in the loops, and it appears as a sickness of scale. High-energy virtual gravitons contribute ever larger corrections, and the integrals diverge as you push the loop momentum higher. The more energy you allow in the loop momentum, the more the calculation refuses to settle. A visual metaphor can make the divergence intuitive. The loop diagram is drawn as a neat circle, then it is filled with brighter and brighter contributions as the scale increases until the circle becomes a glare. The mathematics is saying that the smallest distances dominate, and they dominate too strongly. Divergences are not automatically fatal, and physics has learned to live with them in a disciplined way. In renormalizable theories, infinities can be absorbed into a finite set of parameters, then predictions remain stable across scales. The infinities are reorganized, not ignored, and the theory keeps its explanatory power. Quantum electrodynamics is the classic example, and its success is almost uncanny. Charge and mass are renormalized, and the remaining predictions are finite and extraordinarily precise, even when you include many loop corrections. The electron's magnetic moment matches experiment to more than 10 decimal places, a triumph built on careful handling of loops. That historical triumph shaped expectations. It taught physicists that a theory can be wildly quantum at short distances, yet still yield clean answers when renormalization works. It also made it tempting to believe that gravity would eventually submit to the same strategy. Naive quantum gravity does not behave that way, and the failure is systematic. Each higher-order correction demands new counterterms, with new independent parameters, and the list does not stop. The theory does not close on a small set of measurable quantities, so it cannot make sharp predictions at arbitrarily high energies. That is what non-renormalizable means here, and the phrase carries a specific sting. The theory needs infinitely many knobs to absorb its own infinities, so it loses predictive power as you climb in energy. You can still compute at low energies as an effective theory, but the ultraviolet completion remains unknown. An accessible analogy is repairing a machine with a fixed toolkit, and the analogy is more than cute. If every new breakdown requires a brand new tool, the toolkit never closes, and the method never becomes complete. You can keep fixing problems one by one, yet you never reach a finished, self-contained method. In renormalizable theories, the toolkit is finite, and that finiteness is a kind of miracle. You measure a few parameters once, then you can predict many outcomes across a wide range of conditions. The theory becomes economical because its short-distance behavior is controlled by a small set of principles. In perturbative gravity, the toolkit explodes, and it explodes because gravity couples to energy itself. Every fluctuation, including the virtual ones that fill loop diagrams, gravitates in principle, and the coupling grows with energy. You would need an endless list of measurements to define the theory at all energies. Each new counterterm encodes new sensitivity to microscopic structure, as if the theory is admitting it does not know what spacetime is made of. The divergences are not random, they are structured, and they point to missing degrees of freedom or missing principles. The mathematics is behaving like a detector for the limits of the smooth manifold assumption. This is not a mere technical annoyance, and it is not just a complaint about ugly integrals. It is a sign that the smooth metric expansion is the wrong starting point at the Planck scale, even if it works beautifully at low energies. The perturbative approach assumes a background that remains meaningful down to arbitrarily small distances, and that assumption is precisely what foam calls into question. The foam picture and the divergence picture point the same way, even though they arise from different instincts. Treating geometry as a small fluctuation on a smooth manifold likely misses the true degrees, and the loops are telling you that the ultraviolet is not under control. If spacetime is not fundamentally smooth, then expanding around smoothness may be like expanding around the wrong vacuum. So the failure is two-sided, and it is symmetrical in a revealing way. Quantum field theory assumes a fixed background for locality and time, and general relativity assumes a smooth manifold for geometry, and each assumption is natural within its own domain. Each framework borrows a stability that the other framework refuses to guarantee. At the Planck scale, both assumptions become suspect, and suspicion becomes unavoidable. The vacuum is not just noisy matter, it is noisy geometry, and the noise is not a small perturbation. The object that defines distances, times, and causal order becomes part of the quantum uncertainty. That shift changes what we mean by a point, and points are the atoms of the continuum picture. A point is defined by taking neighborhoods arbitrarily small, but the Planck boundary blocks that limit with operational consequences. When you try to shrink a region beyond a certain scale, the energy required to localize it threatens to create horizons. The documentary can pause on the intuition. A classical point is infinitely sharp, but an infinitely sharp point would require infinitely high momentum modes, and those modes carry energy. Gravity then responds, and the response is not polite. At some point, the attempt to define the point destroys the meaning of the point. If points are not fundamental, locality may be emergent, and emergence is a subtle word. The world could look local at large scales, while being non-local in its microscopic code, and both statements could be true in their proper domains. Locality might be like fluid behavior, real and reliable, yet not fundamental in the underlying molecules. Non-local here does not mean faster than light messages, and it does not automatically invite paradox. It means the fundamental description may not be organized by space-time points at all, even if the effective description is. The basic variables might be relational, algebraic, or combinatorial, with space-time appearing only as an effective approximation. This possibility is mysterious because it reverses our habits, and habits run deep in physics. We usually build physics on space-time, then add fields, but here space-time may be built from something else, and the something else might not look geometric at first glance. The stage may be assembled from the play, rather than the play performed on a pre-built stage. The visuals can reflect that reversal. The grid fades out, replaced by abstract nodes and links. Then the nodes blur into a smooth surface as the camera pulls back. The viewer sees the same world, but the construction order is inverted. Structure first, geometry second. The documentary's conclusion theme begins to take shape, and it becomes more unified with every step. Measurement, geometry, and quantum uncertainty are converging into one problem, not three, and the convergence feels inevitable. The limits of observation are not just practical, because they are tied to the structure of space-time itself. Now connect this to the most dramatic failures of smooth geometry, failures that appear inside Einstein's own equations. General relativity predicts singularities, where curvature becomes infinite and the manifold description breaks, and the prediction is not a minor glitch. These are places where the mathematical model signals its own breakdown, as if the map is drawing a cliff at the edge of its paper. A singularity is not just a large number, and it is not merely an extreme environment. It is a point where the equations stop giving a physical space-time, and geodesics cannot be extended, which is a precise mathematical statement. In plain language, the rules for moving clocks and rulers forward in time no longer produce a consistent continuation. There is also historical weight to this. The singularity theorems of Penrose and Hawking showed that, under broad conditions, singularities are not rare accidents but generic outcomes of collapse and expansion. The theory, when taken seriously, leads you to its own edge. Quantum field theory also hates infinities, though it hates them for a different reason. When infinities appear, quantum field theory demands renormalization or new physics, because infinite answers are not predictions you can compare to data. An infinite cross-section or an infinite energy density is not a result, but a warning. So singularities become a signpost, and signposts are valuable because they tell you where not to drive. They mark where the smooth classical description has been pushed beyond its domain of validity, and where new degrees of freedom must take over. The question is not whether the singularity is real in a naive sense, but what replaces the description that produces it. Black hole interiors are one signpost, and their drama is hidden behind horizons that block direct observation. The early universe is another, where densities and curvatures approach the Planck regime, and where the notion of a classical beginning becomes suspect. In both cases, the theory points toward a boundary where quantum gravity cannot be avoided. If space-time foam is real, it offers a way to reinterpret the signposts without pretending the problem is solved. The singularity may be an artifact of forcing smooth geometry onto a quantum regime, like extending a fluid equation past the scale of molecules. What looks like an infinite spike in curvature might instead be a region where geometry becomes a fluctuating quantum object, no longer describable as a single manifold. That does not solve the problem by itself, and it should not be sold as a quick fix. It tells us where to stop trusting the old map, and where to search for a new one, with new variables and new principles. It also suggests that the true microscopic theory may replace the very language in which singularities are defined. We end this chapter with the core contrast made explicit, because the contrast is the engine of the mystery. General relativity gives a calm, curved continuum, while quantum mechanics gives a restless vacuum that cannot stay quiet, even in principle. One framework assumes differentiable geometry, the other insists on irreducible fluctuations, At low energies, we can keep them separate, and the separation is extraordinarily useful for calculation and for intuition. At Planck scales, vacuum fluctuations gravitate, and the separation collapses in a way that feels almost personal. The vacuum is no longer a background condition, because it becomes a dynamical source of curvature. So the smooth universe is likely a large-scale illusion, even if it is an illusion that works beautifully. Underneath, geometry may fluctuate, topology may flicker, and locality may be a derived convenience, not a starting axiom. The world we navigate could be the averaged face of something far more turbulent. Next, we follow this instability into the places where horizons dominate. We ask how quantum theory behaves when spacetime itself carries entropy and temperature, and why that thermodynamic language keeps returning. The focus shifts from foam in empty space to the thermodynamic character of horizons, where geometry and information become inseparable. We return to the hook with a darker edge, and the warning becomes sharper. Ask for more precision, and the universe may answer with a horizon, even when the target is empty space, and the horizon changes what can be known. The vacuum, when pushed hard enough, may not reveal a finer grain of space, but a boundary that ends the question. The Planck scale is often introduced as a tiny distance, but its real force is logical, almost grammatical. It marks the place where our two best diaries of reality begin contradicting each other in ink, each consistent alone, yet mutually intolerant when read line by line. When we say Planck, we are not only naming a number, we're naming a regime where the rules used to define distance, time, and energy stop agreeing. Chapter 3 framed the hook as an operational threat, not a poetic one, because nature enforces limits with physical consequences. Ask for more precision, and the universe can answer with a black hole, turning your measuring ambition into a trapped region. That is not metaphorical punishment. It is geometry responding to energy concentration. Chapter 4 showed why smooth spacetime is an assumption, not a guarantee. Once vacuum fluctuations gravitate, and the empty vacuum becomes an active source. The vacuum is not a blank stage. It is a restless quantum medium whose bookkeeping can bend the stage itself. Now, we push that boundary into the most dramatic arenas we know. Black holes and the Big Bang are not side stories, not exotic footnotes at the edge of textbooks. They are where general relativity and quantum theory write incompatible accounts of time, causality, and information, accounts that cannot both be literal. If the contradiction is real, it should show itself where gravity is strongest and where quantum rules are strictest. General relativity is a theory of geometry with a strict promise, and it delivers that promise with mathematical precision. Given matter and energy, Einstein's equations determine curvature, and curvature determines motion, so the geometry becomes the engine of dynamics. In that framework, predictability means you can extend geodesics and evolve initial data forward, as though the universe were a well-posed computation. The promise is not only philosophical, it is encoded in the structure of the field equations, which are local and deterministic once the right data are specified. To make that promise concrete, relativity treats spacetime as a differentiable manifold equipped with a metric field, and it assumes that field is smooth enough to support calculus. The metric tells clocks how to tick and rulers how to measure, while the connection tells free-falling objects what straight means. In practice, the metric also defines light cones, so it defines which events can influence which others. If you specify suitable initial data on a slice of spacetime, the equations aim to determine what comes next. This is the classical ideal, a clean pipeline from initial conditions to a unique future. But general relativity also contains a built-in warning label, and it appears not as an anomaly but as a theorem. Under broad conditions, it predicts singularities, where curvature scalars diverge and geodesics end, so the very notion of next becomes undefined. The theory does not merely predict extreme events like high density or strong tides. It predicts the failure of its own spacetime description, as though the diary page tears mid-sentence. The mathematics does not whisper this. It states it with the bluntness of incompleteness. Historically, this was not a casual observation, because it emerged from rigorous work in the 1960s. The singularity theorems of Penrose and Hawking showed that collapse and expansion generically lead to geodesic incompleteness, provided certain energy conditions hold. Those conditions are, in plain terms, assumptions that energy behaves reasonably, so gravity tends to focus geodesics rather than repel them. the message was unsettlingly clean. Singularities are not artifacts of perfect symmetry alone. They are built into the classical logic of curved spacetime. Inside a black hole, classical collapse drives density upward without bound, at least in the idealized description. Tidal forces grow without limit as you approach the central region, stretching and squeezing matter along different directions. In the simplest solutions, curvature becomes infinite at a finite proper time for infalling observers, meaning your own wristwatch reaches an end of classical predictability. Visually, the camera can ride with the infaller, stars distort into bright arcs, then smear into a warped ring as spacetime itself tilts. Even before any infinite point is reached, the geometry begins to behave like a funnel whose walls steepen relentlessly. For a distant observer, the story looks different, and that difference is part of the mystery's texture. Light from the infalling matter is increasingly redshifted, and signals arrive more slowly, as though the collapse freezes near the horizon. The last photons thin into deeper reds, then into radio whispers, then into silence below any detector's patience. Yet the infalling observer crosses the horizon in finite time, noticing nothing locally dramatic if the black hole is large. The same geometry offers two narratives, both consistent, and that duality will matter later. The early universe carries the same signature in reverse, as if time were rewound through a cosmic film reel. Evolve the expanding cosmos backward under classical assumptions, and you reach a state of arbitrarily high density and temperature. The Big Bang singularity is not just a beginning in time, like the first frame of a movie. It is a point where the classical equations stop producing a well-defined continuation, leaving the before unasked and unanswered. In visual terms, galaxies rush together, background light heats from microwave glow to blinding white, and then the film burns through its own celluloid. In both cases, the breakdown is precise, not rhetorical, and the mathematics names it without ambiguity. Geodesic incompleteness means there are world lines that cannot be extended, even though the equations demand extension, so the notion of a complete history fails. The manifold picture runs out of road, and the map provides no next step, even if you keep insisting there must be one. It is the difference between a difficult calculation and a missing definition. Singularities are often misheard as physical points that exist somewhere, like tiny needles hidden in space. Most working physicists treat them differently, because infinities in physics have a familiar smell. Infinities are interpreted as theory failure, signaling missing degrees of freedom, or wrong assumptions about smoothness, continuity, or the variables we chose to describe reality. The point is less like an object and more like an error message. This is how physics has learned to read its own pathologies, and the lesson was learned repeatedly across centuries. When a model yields infinite energy, infinite curvature, or undefined evolution, it is usually not a discovery of literal infinity. It is a diagnostic that the model is being pushed beyond its domain, like a thermometer that shatters when the temperature exceeds its scale. The shattering is real, but it is the instrument that fails, not necessarily the world. Even in classical electromagnetism, the infinite self-energy of a point charge was a warning that point-like was an idealization with consequences. In quantum field theory, naive calculations often diverge, and renormalization teaches us to separate physical predictions from unphysical infinities. Renormalization does not erase the problem by magic. It reorganizes the theory so measurable quantities remain finite, while hidden assumptions are made explicit. The same interpretive habit applies here. A singularity is a signpost that the variables have become the wrong language. The Planck Scale gives a reason for that diagnosis, and it is not merely numerical. If curvature reaches Planckian values, quantum fluctuations of geometry cannot be ignored, because the gravitational field itself becomes a quantum participant. The smooth metric used by classical relativity becomes an approximation, and singular behavior can be an artifact of forcing continuity onto a quantum regime. At that point, the question is not how big is the curvature, but what does curvature even mean when it fluctuates? At the Planck scale, the relevant constants conspire into a set of natural units, and those units are not arbitrary. Combine Newton's constant, Planck's constant, and the speed of light, and you build a length, a time, and an energy where gravity and quantum effects are equally strong. The Planck length is tiny, but the deeper point is the balance of principles because neither framework can dominate. It is the scale where a quantum of action and a quantum of geometry begin to speak the same volume. Black holes add a second ingredient that turns failure into paradox, and it arrives before you ever reach the singularity. They contain event horizons, which are not material surfaces, not shells of matter you could scrape or drill. They are causal boundaries that separate what can influence the outside from what cannot, and that separation is defined by the geometry itself. A horizon is not where gravity is strongest. It is where the causal map folds in a particular way. An event horizon is defined by light cones and global causal structure, not by local density alone. Once formed, signals from inside cannot reach distant observers because every future-directed path points deeper inward. This is not about slow communication or technological limits. It is about which paths exist in spacetime and which paths are simply not allowed. The horizon is a statement about the future, and that global character is part of why it is so slippery. Visually, a horizon is often drawn as a dark circle, but the more faithful picture is a boundary in the space of possible futures. Imagine a swarm of light rays trying to climb outward, and then imagine them tipping inward as the geometry tilts. That tipping is the horizon's essence, a geometric decision about what outward even means. In animation, the cones of light can narrow and lean, until escape is no longer a direction. That causal boundary sets the stage for a conflict with quantum theory, because quantum theory is unusually strict about bookkeeping. Quantum mechanics insists that time evolution, for an isolated system, is unitary, meaning it preserves probabilities and preserves information in a precise mathematical sense. Even when outcomes look random, the underlying evolution is reversible at the level of the full state. The randomness is in our access, not in the fundamental map. In quantum language, information is encoded in the full quantum state, including phases and correlations that no single measurement reveals. A pure state evolves to another pure state under unitary dynamics, like a rotation in an abstract space of possibilities. If a pure state becomes a mixed thermal state with no hidden correlations, unitarity is violated and the theory's core structure cracks. It would be like a perfectly reversible cipher that sometimes deletes letters. At first, horizons look like a classical censorship that quantum theory might tolerate, because hiding is not the same as destroying. You can hide information behind a boundary without destroying it, and the outside observer merely loses access. The global state can still be pure, even if any partial description looks messy and incomplete. In fact, quantum theory expects this kind of partial ignorance, because tracing out inaccessible degrees of freedom produces mixed states. The problem becomes unavoidable when you include quantum fields near horizons, because quantum fields do not sit quietly on curved backgrounds. Quantum field theory on curved spacetime predicts particle creation, and it does so without requiring full quantum gravity. A horizon changes what different observers call vacuum, and that mismatch produces real radiation, detectable in principle far away. The vacuum is observer-dependent when spacetime is curved and time is not globally uniform. This is where Hawking's calculation enters as a turning point, and it is difficult to overstate its conceptual shock. It does not rely on speculative quantum gravity, and it does not require Planck energy collisions. It uses quantum field theory in a classical black hole background, and it yields a concrete prediction that black holes glow. Historically, this arrived in the 1970s, when black holes were still widely treated as mathematical curiosities rather than thermodynamic objects. To appreciate the calculation structure, it helps to remember what vacuum means in quantum field theory. The vacuum is not emptiness, but the lowest energy state consistent with the field's commutation relations, and it contains fluctuations. Those fluctuations are not optional noise, because they are required by the uncertainty principle and by the field's quantum nature. Even in perfect darkness, the fields are never perfectly still. Start with the vacuum near the horizon, where the geometry is strongly curved globally, but can look locally gentle. Quantum fields fluctuate, and fluctuations can be viewed as correlated excitations across nearby regions, even when no particles are present initially. Near a horizon, the separation between inside and outside becomes absolute for causal propagation, and that absolutism matters. A correlation that would normally reunite can be split by the causal boundary. One accessible picture uses pair creation near the horizon, and it survives as an intuition even if the real derivation is more refined. A fluctuation produces two correlated quanta, linked by entanglement in their joint state. One escapes to infinity and is seen as radiation, while the other falls inward, carrying negative energy relative to infinity and reducing the black hole's mass. The horizon becomes a kind of one-way accounting surface, where correlations are divided into seen and lost. The negative energy language can sound mystical, but it's really about how energy is defined for distant observers. In curved space-time, energy depends on time translation symmetry, and near a horizon that symmetry is subtle, the infalling partner effectively subtracts from the black hole's mass, allowing the escaping partner to be paid for without violating conservation. In visual terms, the black hole's shadow remains, yet its mass budget quietly drains. The details are more subtle than the storybook image, and Hawking's derivation uses modes that stretch across the horizon's formation. The key ingredient is that what counts as a vacuum state at early times does not match what counts as vacuum at late times for distant observers. That mismatch produces a steady flux with a temperature set by surface gravity, a geometric quantity tied to the horizon. The temperature is not chosen by hand, it is dictated by the way spacetime accelerates light cones. The conclusion is robust, and it is indifferent to most of the black hole's history. The outgoing radiation is approximately thermal, meaning it resembles blackbody radiation with a temperature. Its spectrum depends mainly on the black hole's mass, charge, and spin, not on the detailed microstate that formed it, and that indifference is the seed of trouble. The radiation looks like it forgot the story of the star that collapsed. Thermal radiation implies temperature, and temperature implies entropy, because thermodynamics is the science of missing information. Bekenstein and Hawking showed that black holes have an entropy proportional to horizon area, not to volume, which is a radical departure from ordinary matter. That area law ties information capacity to geometry, and it hints at microscopic degrees of freedom we do not yet see. The horizon behaves like a ledger whose entries are written in square centimeters, not cubic meters. Historically, Bekenstein's proposal was daring because it treated horizon area as a measure of disorder, even though a black hole looks featureless. Hawking's result then fixed the proportionality constant and linked it to quantum mechanics through Planck's constant. Suddenly, gravity, thermodynamics, and quantum theory were not separate chapters. They were co-authors of the same equation. The black hole became a bridge between disciplines that had long spoken different dialects. The area law also carries a quiet implication about counting, because entropy is a logarithm of the number of microstates. If a black hole's entropy scales with area, then the number of internal configurations grows like an exponential of area, which is enormous. Whatever the underlying degrees of freedom are, they seem to live on the boundary in some effective sense, even if the interior feels spacious. Why should a boundary keep the count for a volume that looks vast from within? Hawking radiation also implies evaporation, and evaporation turns a static geometry into a long, slow process. If a black hole radiates energy, it loses mass, and as it loses mass, its temperature rises, making the late stages hotter. Over extremely long times, an isolated black hole can shrink and eventually disappear, leaving radiation behind and no obvious place for hidden data. The visual can be patient and haunting, a dark silhouette slowly thinning as a faint glow accumulates around it. For stellar mass black holes, the evaporation time is fantastically longer than the current age of the universe, so the process is not a practical laboratory. Yet the paradox is not about experimental convenience, because it is about consistency. If the laws are universal, then even a process that takes eons must make sense in principle. A theory cannot be almost unitary and still be unitary. Now the paradox becomes sharp enough to state in one line, and the line cuts deep. If a black hole forms from a pure quantum state and evaporates into thermal radiation, then pure becomes mixed. That map is not unitary, and quantum mechanics forbids it, because it would erase correlations in a way no closed system should allow. The forbidden step is not subtle. It is a direct violation of the rule that quantum evolution preserves the full informational content. This is not a philosophical discomfort about what we can know, or a complaint about measurement limitations. It is a mathematical inconsistency between two frameworks we trust, each validated in its own domain with extraordinary success. General relativity plus semi-classical quantum field theory seems to predict information destruction, and the word seems is where the fight begins. The semi-classical approximation is powerful, but it may be hiding the very correction that matters. To see why the conflict is unavoidable, track the entanglement, because entanglement is quantum theory's accounting ledger. Early Hawking radiation is entangled with degrees of freedom behind the horizon because the outgoing quanta are born correlated with partners that fall inward. As evaporation continues, more radiation escapes, and the entanglement between radiation and interior grows, like a knot tightening with time. In a visual diagram, the entanglement lines multiply until the page looks like a dense weave. If the black hole fully evaporates, the interior degrees of freedom seem to be gone, at least in the classical picture. The remaining radiation, if truly thermal and uncorrelated, cannot encode the original information, because thermality is a statement of ignorance. The final state looks mixed, even if the initial state was pure, and that is the forbidden transition. The diary would end with a smear where a sentence should be. One can try to evade the conclusion by saying information remains hidden, but the horizon is not a storage locker you can keep after the building is demolished. Hidden where, if the black hole is gone and the spacetime no longer contains an interior region. One can say information is destroyed, but that breaks unitarity and undermines the consistency of quantum theory, including its careful probability rules. If probabilities stop adding up exactly, the entire predictive engine of quantum physics becomes suspect. This is why the information paradox is a Planck Scale problem that reaches outward, like a crack that starts microscopic and then spreads across a window. The naive place to expect quantum gravity is the singularity, where curvature is enormous. Hawking's argument says the crisis can be diagnosed from the horizon outward, using low curvature regions where classical geometry looks trustworthy. That outward reach is the clue that the conflict is not only about violent interiors. That outward reach is what makes the paradox so valuable, because it turns black holes into conceptual laboratories. We cannot build Planck energy particle accelerators, but the universe builds horizons for free. A large black hole can have gentle curvature at its horizon, so any resolution cannot hide behind extreme conditions alone. The paradox demands a principle-level fix, not merely a high-energy patch. The stakes can be stated as a trilemma, and each branch demands a sacrifice. Either quantum mechanics fails and evolution is not unitary, implying fundamental information loss, or general relativity's classical horizon picture fails in a quantum setting, meaning the smooth boundary is not what we think, or locality fails and information escapes in a non-local way, violating the usual separation of causes and effects. The trilemma is not a rhetorical flourish. It is a tight constraint produced by combining entanglement, causality, and thermality. Each option carries a cost that reshapes the foundations, and none is cheap. Giving up unitarity threatens probability conservation and the structure of quantum theory, including the way amplitudes add and cancel. Giving up the classical horizon threatens the equivalence principle and the smoothness of spacetime for infalling observers. Giving up locality threatens the organizing principle of quantum field theory, where influences propagate through nearby points. Which principle is negotiable, and which one is the hidden author of the diary? The paradox also connects back to the measurement trap, but now the trap is informational rather than energetic. In Chapter 3, horizons appeared as the universe's reply to extreme localization, because concentrating energy too sharply makes a trapped surface. Here, horizons appear as the universe's reply to extreme bookkeeping about information, because insisting on unitarity forces hidden correlations to reappear. In both cases, the boundary is causal, not merely energetic, and causality is the stage where the contradiction plays. The same geometry that blocks signals also blocks naive explanations. One proposed resolution is remnants, and it has the appeal of a simple ending. The black hole evaporates down to a Planck Scale object that does not disappear, leaving a tiny survivor behind. Information remains stored in the remnant, preserving unitarity, while the radiation can remain nearly thermal. The image is cinematic. The vast darkness collapses into a final ember, a speck against the starfield. Remnants pay a steep price, and the price is not aesthetic but dynamical. They must have an enormous number of internal states to encode arbitrary initial information, because the initial black hole could have been arbitrarily large. That can lead to uncontrolled production in ordinary processes, because an effectively infinite state density can destabilize low-energy physics and overwhelm predictions. A theory that permits limitless hidden storage risks, turning the vacuum into a factory for remnants. Another proposal is information leakage in the radiation, and it keeps the ending but changes the middle. The radiation is not exactly thermal, even if it looks thermal to leading order and to coarse measurements. Subtle correlations, invisible in Hawking's leading approximation, carry the information out over time, so the final radiation state is pure even if it masquerades as noise. The key is that thermal might be an approximation that hides a delicate pattern. Leakage preserves unitarity, but it demands a mechanism, and mechanisms must respect what we already know about horizons. In semi-classical reasoning, the horizon region looks locally like empty space, especially for a large black hole where curvature is small. If nothing special happens there, it is hard to see how information escapes without violating locality, because the interior is causally disconnected. The puzzle becomes, where do the correlations live while the horizon still behaves like a one-way boundary? A related family of ideas adds horizon-scale quantum structure, and it does so with careful ambiguity. The horizon is not a featureless boundary, and quantum gravity replaces it with degrees of freedom that can imprint correlations on outgoing radiation. The modification might be delicate enough to preserve the infalling experience, yet powerful enough to change the global bookkeeping. Visually, the horizon can be shown as a shimmering layer, almost invisible, whose texture appears only when the camera lingers. This can take many forms in the literature, and the diversity reflects how constrained the problem is. Some versions keep the horizon smooth for infalling observers, while encoding information in subtle, possibly non-local correlations that only appear in the full quantum state. Other versions make the horizon itself a quantum membrane with real dynamics, so the boundary becomes a participant rather than a passive line. The common theme is that the classical boundary may be too clean to be true. Black hole complementarity is an attempt to keep both stories without direct contradiction, and it treats the horizon as a kind of translation device. Outside observers describe information as stored on or near the horizon and returned in radiation, as though the horizon were a hot surface. Infalling observers describe nothing special at the horizon, and information passing inward, as though space continues normally. The two accounts are not both globally literal, but they might both be operationally consistent. Complementarity claims the two descriptions cannot be compared operationally, because no single observer can verify both copies of the information. No observer can both collect all the Hawking radiation and also cross the horizon to check the interior partner, at least not without violating causal constraints. The no-cloning principle is not violated in any measurable way, but the cost is a controlled kind of non-locality, and a new rule about what counts as a consistent global description. The diary becomes contextual, as though the ink changes depending on who reads it. The firewall argument challenges that compromise, and it does so by sharpening the entanglement logic. If late radiation must be entangled with early radiation to preserve unitarity, then it cannot also be entangled with interior partners in the usual way. Monogamy of entanglement forces a choice, because a quantum system cannot be maximally entangled with two independent systems at once. The bookkeeping cannot be satisfied in three places simultaneously. If you keep unitarity and standard quantum rules, the horizon cannot remain vacuum-like for infalling observers, at least not in the naive semi-classical picture. A high-energy barrier, a firewall, appears at or near the horizon, breaking the equivalence principle and making the horizon a special place. The cost is dramatic because it replaces the gentle crossing promised by relativity with a violent boundary. The visual is stark. The smooth black edge becomes a bright, lethal ring. Other proposals shift the problem to the singularity, where we already expected classical physics to fail. Information might pass through a quantum region and re-emerge in a new spacetime, or be encoded in a bounce replacing the classical singularity. These ideas aim to preserve unitarity by changing the deep interior, turning the end of geodesics into a transition rather than a termination. They keep the horizon calm, but they ask the center to do the heavy lifting. But Hawking's setup makes a warning unavoidable, and the warning is about where the paradox lives. The paradox is visible without touching the singularity, because it is driven by horizon causality and quantum entanglement. Those ingredients can involve regions of low curvature, so the resolution cannot be postponed to the deepest, darkest center alone. If the contradiction is already written at the horizon, the singularity cannot be the only editor. This is where the Planck Scale stops being a tiny distance slogan and becomes a global consistency demand. Entanglement links far separated regions, and the horizon organizes those links into inside versus outside bookkeeping. Quantum correlations can make microscopic physics relevant at macroscopic scales, because the distinction between purity and mixedness is global, not local, and global constraints can reach far. The Planck Scale becomes a reach of logic, not just a reach of length. The key tension can be restated in the documentary's mysterious tone, because the contradiction reads like a narrative mismatch. General Relativity writes a diary where horizons hide and singularities end the story, as though some pages are sealed and others are torn away. Quantum theory writes a diary where evolution never erases a line, even if it scrambles the handwriting into patterns. When you read both diaries together, the pages do not match, and the mismatch is not a metaphor. It is a demand for a third language that can translate both. We can sharpen the contradiction with one operational question, the kind that refuses to be soothed by philosophy. If information is preserved, then where is it encoded during evaporation at each stage of the process? If it is encoded in the radiation, then how does it get out past a causal boundary that forbids outward influence? If it is encoded at the horizon, then what replaces the smooth local vacuum that infalling observers are supposed to see? The question is simple to ask, and brutally hard to answer. The area law deepens the mystery rather than resolving it, because it suggests a new architecture for degrees of freedom. Entropy scaling with area suggests that the fundamental degrees of freedom are not arranged like ordinary local fields in a volume, where each small region carries its own independent bits. It hints that space-time geometry may be emergent from a more economical information structure, where boundaries do the counting. The horizon looks less like a border and more like a storage rule. That hint is not merely numerology, because thermodynamics is a language of universality. When very different microscopic systems share the same macroscopic laws, it usually means we are seeing a deep principle rather than an accident. So when black holes obey a thermodynamic law with an area entropy, it invites a question. What microscopic atoms of geometry are being counted by that area? And if they are being counted, why does the count ignore the interior volume so completely? This is also where Chapter 4's foam returns with new meaning, because the horizon is a geometric object that might not survive quantization intact. If smooth spacetime is an approximation, then a horizon might also be an approximation, defined only in the coarse-grained limit. The classical boundary could be replaced by a quantum region, whose thickness and structure are set by Planckian physics, even if it looks sharp from far away. From a distance, the line is crisp. Up close, it may be a restless band of quantum uncertainty. Yet the paradox insists that any such structure must be consistent with low-energy observations, which is a severe constraint. Far from the black hole, physics looks like ordinary quantum field theory in nearly flat space, and it works with astonishing accuracy. Near the horizon, curvature can be small for large black holes, so any modification must be subtle or deeply non-local, hiding in correlations rather than in obvious fireworks. The fix must be powerful enough to save unitarity, yet quiet enough to avoid contradicting everything else. That is why the information paradox is so valuable as a guide, even before it is solved. It is a consistency check that probes quantum gravity without requiring Planck energy experiments, because it forces principles to confront each other. It forces us to confront whether locality, geometry, or unitarity is the emergent concept, and which one is the deeper author of the diary. The paradox is a compass made of contradictions, and it points toward whatever theory can keep the ledger balanced. The Big Bang singularity carries a parallel lesson, and it echoes the same logical structure. Classical relativity predicts a beginning where the equations stop, and the stop is not a choice but a consequence of extrapolation. Quantum theory suggests evolution should be well defined, even if the variables change, so undefined feels like a sign that we chose the wrong description. The early universe becomes another diary entry where the classical story ends in an undefined symbol. In cosmology, the horizon is not the same as a black hole event horizon, but causal boundaries still matter for what can influence what. Inflation, particle horizons, and the growth of entanglement shape what information can be shared across the universe, and what remains forever out of contact. The Planck era is not just hot and dense. It is where the meaning of time evolution and initial conditions becomes ambiguous, because the usual clock and ruler picture may not apply. Even the idea of a single global now can become a questionable convenience. Run the cosmic film backward, and the wavelengths of quantum fields are squeezed, while energies rise and interactions intensify. The same vacuum fluctuations that seemed like gentle foam in Chapter 4 become amplified players, because gravity couples to energy at every scale. If spacetime itself fluctuates, then initial conditions may not be a single clean surface, but a quantum state with many competing geometries. The universe's first page may not be a page at all, but a superposition of drafts. Both arenas point to the same conclusion, and the conclusion is more about principles than about specific objects. Singularities and information loss are not separate problems, as though one belonged to cosmology and the other to black holes. They are different faces of the same Planck Scale breakdown, where smooth geometry and local quantum fields cannot both be fundamental in the naive way we learned. The contradictions are telling us that our categories may be emergent, not primary. We should be clear about what the paradox does and does not say, because mystery can tempt overstatement. It does not prove a specific resolution, and it does not force one particular theory of quantum gravity. It proves that the naive combination of classical horizons with quantum unitarity and locality cannot be the final story, because the trio cannot coexist without contradiction. Something must give, or something deeper must unify them. So the chapter's climax is a controlled contradiction, not a final answer, and that control is what makes it useful. General relativity predicts singularities where predictability ends and curvature diverges, and it does so under broad, realistic conditions. Quantum mechanics demands unitary evolution where information is never destroyed, and it does so with mathematical rigidity. Hawking radiation makes the conflict concrete by turning horizons into thermodynamic emitters, so the paradox is not hypothetical. It is a calculation that turns philosophy into a quantitative crisis. The paradox also reframes the opening hook, tying the earlier operational limit to a deeper accounting problem. The universe answers sharper questions with black holes, and black holes answer back with radiation, a faint glow against the dark. The reply is not silence. It is thermal noise that seems to erase the very information the question tried to preserve, as though the universe was smudging its own ink. And if the ink is smudged, we have to ask whether the page is made of something other than paper. Now we pivot from diagnosis to direction, because contradictions are only valuable if they point somewhere. The information paradox suggests the Planck scale is not confined to tiny distances, like a microscopic border you never touch. Through entanglement and quantum correlations, Planckian consistency conditions can reach up to macroscopic horizons, turning large black holes into mirrors of quantum gravity. The smallest scale becomes a rule that governs the largest shadows. Next, we follow that reach into the idea that geometry itself may be encoded in quantum information. We ask whether spacetime is built from entanglement patterns, and whether horizons are where the code becomes visible, like seams in a fabric that only appear when stretched. The Planck wall is not only a limit of instruments, it is a limit of the concepts our instruments assume. When we build detectors, we quietly assume a background stage, space as a smooth grid, and time as a steady parameter. At the Planck scale, those assumptions stop being innocent, because the act of localization becomes gravitational. We reached it by insisting on sharper questions. Nature answered with horizons, thermality, and missing pages in the diary. Push energy into a smaller region, and by general relativity, you increase curvature until a trapped surface forms. Push too far and the question itself collapses into a black hole, an answer shaped like a boundary. The image is stark in the mind's eye. A beam tightens, the focal spot shrinks, and then the scene blurs behind a dark rim. It is as if the universe draws a circle around our curiosity and says, "No finer." The Planck wall is not merely a practical barrier, because it is a consistency condition between quantum uncertainty and gravitational back reaction. Now the story turns from diagnosis to blueprints. If spacetime breaks, what replaces it underneath? We are no longer only cataloguing paradoxes, because paradoxes are the pressure that forces new architecture. The question becomes constructive. What mathematical structure can carry quantum rules while producing gravity as a low-energy limit? The goal is precise even when the path is not. We need a theory that is quantum and includes gravity. Quantum here means amplitudes, superposition, and a unitary evolution that preserves total probability. Includes gravity means it reproduces the equivalence principle, the bending of light, and the dynamical geometry encoded by Einstein's equations. It must reduce to general relativity when curvature is gentle and scales are large. It must reduce to quantum field theory when gravity is weak. Those requirements sound modest, yet they are brutally constraining, because they demand two different languages to be dialects of one deeper grammar. In the overlap regime, where both should apply, the theory must not contradict either set of tested predictions. It must tame ultraviolet divergences without infinite new parameters. It must resolve singularities without hiding them behind undefined words. Ultraviolet divergences are not just technical annoyances, because they signal that we are multiplying quantities at arbitrarily short distances. Singularities are worse. They are places where the classical theory stops giving answers, and where the very notion of place becomes ambiguous. It must keep information accounting consistent with quantum unitarity. It must explain why horizons carry entropy and temperature. The puzzle is sharp because thermality suggests loss of detail, while unitarity forbids true erasure. The Bekenstein-Hawking formula, with entropy proportional to area, is a flashing sign that gravity counts degrees of freedom differently than ordinary field theory. This is the climax chapter because the candidates are bold. Each claims a different answer to what is fundamental. Some change the ingredients, some change the recipe, and some change what we mean by kitchen altogether. Each blueprint is a wager about which intuitions survive when we stop treating spacetime as a given. String theory begins by changing the smallest building block. Point particles are replaced by one-dimensional strings. The shift sounds small, yet it rewrites the short-distance story, because a string cannot probe a point without spreading its interaction along a finite length. In visuals, a dot becomes a filament, and the filament becomes a vibrating line drawn across a dark, empty background. A string can vibrate in many modes. Each mode appears as a particle with specific mass and spin. The mathematics resembles a musical instrument, where harmonics correspond to quantized excitations, except the instrument is a relativistic object in spacetime. Some modes behave like familiar matter, some like force carriers, and some only appear at energies far beyond current accelerators. One mode is special because it is unavoidable. The spectrum contains a massless spin-2 excitation that behaves like a graviton. Spin-2 is not a decorative label, because it dictates the universal way the particle couples to energy and momentum. In quantum field theory, a consistent massless spin-2 field essentially forces the nonlinear structure of general relativity. Gravity is not added as an afterthought in this picture. It emerges from the same quantum object that produces matter and forces. That is one reason string theory felt historically like an unexpected gift. A framework built for hadrons in the 1960s later reappeared as a candidate for quantum gravity in the 1970s. The graviton was not inserted by hand. It was hiding in the vibration spectrum. The extendedness of strings changes the ultraviolet story. Interactions are smeared over a length scale rather than localized at a point. In a Feynman diagram picture, sharp vertices soften into smooth worldsheet interactions, and that geometric smoothing can regulate the violent high-energy behavior that plagues point-particle gravity. The intuition is simple in plain language. A string cannot hit with an infinitely sharp punch. That smearing softens high-energy scattering. It hints at a built-in cutoff that can cure the worst divergences. The theory replaces certain divergent integrals with finite ones, because the worldsheet description effectively averages over short-distance structure. This does not mean every calculation is easy, because the bookkeeping becomes more intricate, yet the ultraviolet sickness is less severe. Strings also force a new kind of geometry. Consistency typically requires extra dimensions beyond the familiar four. The requirement is not aesthetic. It comes from demanding that quantum symmetries remain intact and that probabilities remain well defined. In the simplest superstring theories, the critical dimension is 10, and the extra 6 must be accounted for. Those dimensions are not optional decoration. They are demanded by quantum consistency conditions like anomaly cancellation. Anomalies are quantum breakdowns of classical symmetries, and in gauge theories they can destroy consistency by violating charge conservation or unitarity. In string theory, the demand that anomalies cancel can dictate allowed gauge groups and constrain the dimensionality of spacetime, so the theory must explain why we do not see them. The standard move is compactification into tiny curled shapes. The camera, in a visual metaphor, zooms into a seemingly smooth line and reveals a hidden circle wrapped around each point. A dimension can be present, and yet invisible if it is compact and extremely small. Compactification is not a single choice. Many internal geometries are possible, and each choice shapes low-energy physics. The internal space can be a torus, a more intricate calabi, Yau manifold, or other constructions with specific curvature and topology. Each option changes how strings vibrate, and therefore changes the effective particles and interactions we observe. The size and topology of compact dimensions determine gauge symmetries and particle spectra. The geometry becomes a generator of forces. In practical terms, the way fields wrap around cycles in the compact space can produce gauge bosons, while the shape of the space can control coupling constants and the number of particle families. Geometry stops being a passive container and becomes an active source of physical law. This is where the blueprint feels powerful and frustrating. It can produce rich structures, yet it also produces a vast landscape. The landscape is not merely many solutions, it is many self-consistent low-energy worlds, each with different constants and symmetries. The visual becomes a star map of possibilities, dense with points that each claim to be a universe. The landscape is a map with too many cities. It raises a hard question about prediction and selection. If the fundamental theory allows an enormous number of vacua, then we must ask what picks ours and what counts as an explanation. Is the selection dynamical, historical, environmental, or something we have not yet learned to compute? String theory also attacks the black hole puzzle directly. It treats black holes as quantum objects with microstates. The key move is to identify configurations of branes and strings that, at strong coupling, look like black holes with horizons. At weak coupling, the same configurations can be counted explicitly, like counting arrangements in a statistical ensemble. In certain supersymmetric and near-extremal cases, the microstates can be counted. The count matches the Bekenstein-Hawking area entropy. Supersymmetry helps because it protects quantities as the coupling changes, allowing a calculation in a tractable regime to remain valid in a gravitational regime. The match is precise enough to be more than coincidence, because it reproduces the correct dependence on charges and parameters. That success is not merely numerology. It shows that horizon entropy can arise from ordinary statistical counting in a quantum theory. Entropy, in this view, is not mystical. It is the logarithm of the number of microscopic configurations compatible with macroscopic data. The area law then becomes a statement about how many configurations gravity hides behind the horizon description. It suggests the horizon is not a featureless boundary. It is a coarse-grained description of many microscopic configurations. The smooth classical geometry is like a thermodynamic surface, meaningful for large-scale probes but blind to the underlying microstructure. The horizon behaves like a membrane because we are averaging over details we cannot resolve. In these examples, information is not destroyed. It is hidden in degrees of freedom that look geometric only after averaging. The radiation can be thermal in a coarse sense while still carrying subtle correlations in its fine-grained quantum state. The bookkeeping is demanding because the correlations are distributed across many quanta rather than stored in any single particle. Yet the success is partial and conditional. It works best in special limits that are not obviously the astrophysical universe. Many counted black holes are extremal or near-extremal, often with high symmetry and carefully chosen charges. The real black holes in galaxies are messy, rotating, and formed from collapsing matter, so the bridge from idealized models to nature remains incomplete. It also leans on a background framework. Many calculations start with a chosen spacetime and quantized strings on that stage. This method is technically effective because it gives a stable arena for perturbation theory, where one expands around a known geometry. The cost is conceptual. The geometry is partly assumed rather than fully derived. That approach is powerful for computation. It also raises a philosophical tension with general relativity. General relativity says the stage is dynamical, shaped by energy and momentum, and not fixed in advance. A fixed background can feel like a return to the very split that broke at Planck scales. Matter here, geometry there. Loop quantum gravity begins from the opposite instinct. It refuses to assume a fixed stage at the start. The program takes Einstein's insights seriously. Geometry is a field, and fields can be quantized. Historically, this line grew from canonical quantization approaches and the reformulation of gravity in terms of connection variables. The core move is to quantize geometry itself. The gravitational field is rewritten in variables suited to quantization. Instead of the metric as the primary variable, one uses a connection and its conjugate momentum, closer in spirit to gauge theories. This shift allows the use of techniques from quantum gauge fields, but applied to spacetime geometry. In this framework, space is not a continuum of points. It is built from networks of quantum relations called spin networks. The visual is a web of lines and nodes suspended in darkness, like a constellation drawn with luminous threads. Space becomes a graph-like structure, where adjacency is defined by connections rather than coordinates. Edges and nodes carry quantum numbers. Those numbers determine discrete spectra for geometric quantities like area and volume. When an edge punctures a surface, it contributes a quantum of area, and the total area is a sum over punctures. The discreteness is not like a lattice placed by hand. It is a spectrum emerging from quantization, similar to energy levels in an atom. Discreteness is not imposed by hand. It arises from the representation theory of the underlying gauge structure. The quantum numbers label representations, and the allowed values come from the mathematics of the group. In plain terms, geometry has allowed notes, and not every value is permitted at the smallest scales. This provides a candidate for the atoms of geometry. It offers a natural way to avoid ultraviolet infinities. If there is a smallest non-zero area and volume, then integrals that assume arbitrarily small regions no longer make physical sense. The Planck length becomes not only a unit, but a threshold where the continuum approximation breaks down. If area and volume come in quanta, the continuum limit becomes emergent. The Planck length becomes a scale of granularity. The smooth space we experience would then be like a fluid description of a molecular medium, accurate when we average over many quanta. The documentary camera can pull back from the web until it blurs into a continuous landscape. Loop quantum gravity also confronts singularities. In simplified cosmological models, the Big Bang can be replaced by a quantum bounce. The classical equations drive density and curvature to infinity, but quantum geometry modifies the effective dynamics at extreme conditions. The result is a turnaround, where contraction transitions into expansion without an infinite spike. The bounce is a structural claim. Quantum geometry generates repulsive effects at extreme density, preventing infinite curvature. The word repulsive can mislead, so the plain language idea is safer. Quantum corrections change the relationship between energy density and curvature. At very high density, the effective equations can reverse the classical trend, avoiding the singular point. Similar ideas appear in black hole interior models. The classical singularity may be replaced by a transition region. Instead of a terminal end of spacetime, the interior could contain a quantum domain where geometry continues in a different form. The visual becomes a collapsing tunnel that, rather than pinching to nothing, opens into a new corridor of geometry. These results are promising but not final. They depend on symmetry reductions and choices about dynamics. Symmetry-reduced models are valuable because they are solvable, yet they omit many degrees of freedom that might matter in the full theory. The hardest part is defining and controlling the quantum dynamics without losing the theory's background-independent character. The theory's challenge is also clear. Recovering smooth space-time and standard quantum fields at large scales is technically hard. One must show how classical geometry emerges, how gravitons appear as approximate excitations, and how familiar field theories live on the emergent background. Without that recovery, discreteness remains an elegant micropicture without a proven macro world. Connecting to particle physics is also difficult. The framework does not automatically produce the standard model spectrum. It can incorporate matter, but it does not naturally generate the specific gauge groups, masses, and family structure we observe. That gap is not a small detail, because a quantum gravity theory must ultimately coexist with the particle world. So the contrast between strings and loops is not only technical, it is a contrast in what each treats as primary. One begins with extended objects moving in a higher dimensional arena, then seeks our world as a particular vacuum. The other begins by quantizing the arena itself, then seeks matter and forces as inhabitants of the resulting quantum geometry. Strings treat matter and geometry as excitations of a common object. Loops treat geometry as the first quantum system. The difference shapes intuition about what is real at the bottom. Is the fundamental entity a string in space-time, or a network from which spacetime is built? The two pictures sometimes feel like they are looking at the same mountain from opposite sides. Strings often compute with background dependence. Loops aim for background independence as a guiding principle. Background dependence can be a tool, yet it risks missing a regime where the background itself fluctuates violently. Background independence honors relativity's lesson, yet it can make calculations so hard that contact with experiment becomes elusive. background dependence is not automatically wrong. It can be a practical approximation that becomes exact only in special limits. In ordinary physics, we often expand around a fixed solution to capture small fluctuations, and that strategy can be legitimate. The question is whether quantum gravity allows a controlled expansion that does not secretly assume what it must explain. Background independence is not automatically sufficient. It can preserve the spirit of relativity while leaving dynamics under-constrained. A theory can be elegant and still fail to generate the correct low-energy world. The blueprint must not only avoid contradictions, it must build the familiar universe as an emergent, stable phase. Both programs are trying to answer the same Planck Scale warning. The smooth manifold and local fields cannot both be fundamental. If we insist on fields defined at every point, we inherit ultraviolet infinities and singularities. If we insist on smooth geometry at arbitrarily small scales, we collide with quantum uncertainty and black hole formation. Now, a third idea enters, and it changes the tone. It suggests we have been asking the wrong question about what spacetime is. Instead of quantizing geometry directly, spacetime might emerge from quantum information. Geometry might be a code written in entanglement, and the where of physics might be secondary to the who is correlated with whom. This idea is motivated by the area law of black hole entropy. If entropy scales with area, degrees of freedom may live on boundaries. In ordinary systems, entropy usually scales with volume, because more space means more independent microscopic states. The black hole's area scaling is therefore a provocation, hinting that gravity compresses information into a boundary description. The holographic principle captures that suspicion. The information in a region can be encoded on its boundary with roughly 1 bit per Planck area. The statement is radical, yet it is also precise enough to guide theory building. It suggests that the maximal information content of a region is limited by surface area, not by bulk volume. Holography is not only a slogan, it has a concrete realization in the ADS-CFT correspondence. Born from string theory in the late 1990s, the correspondence proposes a duality between two very different descriptions. The duality is not an analogy, it is an equivalence, where calculations on one side translate into the other. ADS-CFT claims an equivalence between a gravity theory in a bulk spacetime and a quantum field theory on its boundary. The bulk is an anti-de Sitter space, a curved geometry with a boundary at infinity, while the boundary theory is a conformal field theory without gravity. The visual is a cylinder-like boundary encasing a deeper interior, like a shell whose surface data somehow generates depth. In this duality, gravity and geometry are not fundamental in the same way. They are emergent descriptions of a non-gravitational quantum system. The boundary theory has ordinary quantum degrees of freedom, operators, and states, and its evolution is unitary. The bulk geometry appears as an effective description of certain collective patterns in those boundary degrees of freedom. The boundary theory is ordinary quantum mechanics with unitarity. The bulk black hole information problem becomes a bookkeeping problem with a guaranteed answer. If the boundary evolution never loses information, then the bulk process it represents cannot truly lose information either. The paradox is not dismissed, it is relocated into the translation dictionary, so holography offers a sharp hint. If the boundary theory is unitary, the bulk process must be unitary too. That hint is powerful because it is not a philosophical preference. It is a mathematically controlled statement in a specific setting. It tells us that semi-classical reasoning about horizons must be missing degrees of freedom or miscounting correlations. This does not automatically explain how information escapes a horizon. It says the horizon story must be incomplete or encoded differently. The escape might not look like a message flying out of the interior, because the interior itself may be an emergent bookkeeping device. The deeper question becomes, what does inside mean when the fundamental description lives on the boundary? Entanglement becomes the key variable. In many holographic settings, entanglement entropy is related to geometric areas in the bulk. The Ryu-Takayanagi relation and its refinements connect the entropy of a boundary region to the area of a minimal surface in the bulk. The formula reads like geometry, yet it computes a quantum information quantity. The relation suggests a dictionary. The amount of entanglement in the boundary state determines the shape of spacetime in the bulk. Change the entanglement pattern and the bulk geometry responds, as if spacetime were elastic under informational strain. The camera can show a boundary lattice of qubits whose connecting lines thicken, while a bulk surface swells into shape. Geometry becomes a measure of quantum correlation. Distance becomes a statement about how strongly degrees of freedom are entangled. Two regions that share many correlations behave as if they are close, while weakly correlated regions behave as if they are far apart. In plain language, near may mean highly entangled, not adjacent in a pre-existing space. This reframes the earlier chapters. If the metric fluctuates, perhaps the metric is not a fundamental operator at all. Perhaps what fluctuates fundamentally is entanglement structure. The smooth metric is a coarse summary of that structure, like temperature summarizing molecular motion without tracking each molecule. The idea has a dramatic consequence for locality. If geometry is built from entanglement, then local neighborhoods are emergent patterns. Locality can work extremely well at large scales, because the emergent geometry can be stable and robust, yet locality can fail subtly when entanglement patterns are rearranged. Even if no signal travels faster than light, that failure would not look like simple, faster than light signaling. It would look like the breakdown of factorization into independent subsystems. In quantum theory, we often assume we can split the world into parts, each with its own Hilbert space, and then tensor them together. If spacetime itself depends on entanglement, that clean split may be only approximate. This is where the Planck wall becomes a message. Space might be an approximation that fails when we demand infinite resolution. The wall is not only a barrier in energy, it is a warning about categories. Perhaps point and distance are emergent conveniences, reliable for atoms and planets, but not for the deepest bookkeeping of reality. The opening hook returns with new meaning. Ask a sharper question, and the universe answers with a black hole. In the emergent view, the black hole is not only an obstacle, it is a place where the code is exposed, because the area law and thermal radiation are direct outputs of the underlying information accounting. The horizon entropy is a clue about the number of degrees of freedom. The thermal radiation is a clue about how coarse graining hides correlations. Hawking radiation looks thermal because we trace over inaccessible degrees of freedom, producing a mixed state for the outside observer. The fine-grained state can still be pure, yet the purity is distributed in correlations too subtle for semi-classical approximations. Even the firewall debate becomes a clue. It forces us to decide which principle is emergent, the smooth horizon or strict locality. The debate sharpens the tension between the equivalence principle, which predicts a calm horizon for infalling observers, and quantum monogamy constraints on entanglement. If the paradox is real, then at least one cherished assumption must be an approximation. Now the narrative adds a more speculative bridge. It is the ER equals EPR conjecture. EPR names entanglement between separated systems. ER names an Einstein-Rosen bridge, a wormhole connecting regions of spacetime. The conjecture suggests a link between them, as if entanglement were the microscopic thread from which connectivity is woven. The conjecture suggests a link between them. Entanglement might be the microscopic origin of spacetime connectivity. It does not say we can travel through ordinary entanglement. It says the mathematical structure of connection may be the same, and that certain entangled states can be represented geometrically as wormhole-like linkages. This is narrative intrigue because it unifies themes. Entanglement is the quantum ledger, and wormholes are the geometric shortcut. If they are related, then geometry is literally a shadow of correlation. Spacetime becomes a network of quantum relationships, and the bridges are not tunnels through space but patterns in the underlying state. This also reshapes the information paradox. Information could escape without violating unitarity, because the inside and outside are not independent systems. If the Hilbert space does not factor cleanly into interior and exterior, then the usual argument for information loss changes. The horizon can be a useful effective boundary, while failing to be a fundamental separation. The price is that locality is approximate. The causal boundary might be real for low-energy probes, yet porous in the full quantum description. That porosity would be invisible in semi-classical calculations. It would appear only in subtle correlations across many degrees of freedom, correlations that are suppressed for ordinary observations. So the three approaches begin to rhyme. Strings soften ultraviolet behavior and count microstates in special black holes. Loops quantize area and volume and suggest bounces that replace singularities. Holography makes geometry a derived concept from entanglement, and it offers a setting where unitarity is manifest. None of these frameworks is a finished map. Each solves some problems while opening new ones. The history of physics is full of such moments, where partial blueprints compete and cross-pollinate. The deeper question is whether these are rival roads or different projections of a single underlying structure. Strings face the landscape and the challenge of unique predictions. Loops face the challenge of recovering known physics and computing dynamics. Emergent spacetime faces the challenge of generality. ADS CFT is powerful, yet our universe is not obviously ADS, so we must ask how much of the lesson survives in more realistic cosmologies. All face the same experimental silence. The Planck Scale is remote, and direct tests seem impossible. The energies are so high, and the length so small that no human-made collider can reach them. Yet physics has often advanced by finding indirect signatures, where deep structure leaks into accessible phenomena. Yet the chapter cannot end in pure abstraction. The documentary must pivot toward what the universe might let us measure. The camera must leave the chalkboard and return to the sky, to detectors, and to laboratories where quantum control is becoming exquisite. The question becomes practical without becoming shallow, because the stakes are foundational. So we ask a practical question. If spacetime is quantized or emergent, what signatures could leak into accessible scales? The answer is not a single smoking gun, because quantum gravity effects may be small and entangled with ordinary physics. Still, there are plausible windows where amplification occurs, especially in the early universe and in strong gravity astrophysical events. Some signatures would be cosmological. The early universe may carry imprints of quantum gravity in primordial fluctuations. Inflation, if it occurred, stretched microscopic quantum fluctuations to cosmic scales, turning quantum noise into the seeds of galaxies. If quantum gravity modified the initial conditions or the propagation of fluctuations, it could leave patterns in the cosmic microwave background or in primordial gravitational waves. Some signatures would be astrophysical. Black hole mergers might reveal subtle deviations in ringdown or horizon behavior. The ringdown is governed by quasi-normal modes, like the dying tones of a struck bell, and those tones depend on the near-horizon geometry. If the horizon is replaced by microstructure, or if boundary conditions differ from classical expectations, tiny echoes or frequency shifts could appear, though the data analysis is delicate. Some signatures could be particle physics adjacent. Extra dimensions could modify gravity at short distances or produce missing energy signatures. If additional dimensions are large enough, gravity could deviate from the inverse square law at submillimeter scales, and collider events could hint at energy carried away into the extra-dimensional bulk. The constraints are already strong, yet the possibility remains a concrete link between geometry and experiment. Some signatures could be quantum information flavoured. Entanglement and coherence experiments might test whether gravity can carry quantum correlations. The key is not to reach Planck energies, but to place masses in quantum superpositions and see whether their mutual interaction produces entanglement. If the gravitational field can mediate entanglement, then it cannot be purely classical in the usual sense. This is the surprising possibility. Tabletop experiments may probe aspects of quantum gravity without reaching Planck energies. The setups are visually modest. Micron-scale masses, interferometers, cryogenic shields, and painstaking isolation from noise. Yet conceptually they aim at a deep question. Is gravity a quantum channel, capable of transmitting phase information? If gravity can entangle two masses, then gravity must be quantum in some sense. That would be a direct test of a foundational claim. It would not tell us whether strings or loops are correct, but it would rule out broad classes of semi-classical hybrids. It would also tighten the logic of the Planck wall, showing that quantum structure is present even in weak fields. If spacetime is emergent, then noise or decoherence might reveal its microstructure. The challenge is to separate signal from ordinary environment. Any observed loss of coherence must be distinguished from electromagnetic coupling, thermal photons, vibrations, and mundane laboratory imperfections. The experimental art is to build a system where gravity is the dominant remaining interaction, and where alternative explanations are systematically excluded. We end by returning to the central question. Why do quantum mechanics and general relativity fail at the Planck scale? Because the failure is not only a clash of equations, it is a clash of what we think space and time are and of how we define an event when measurement itself gravitates. The blueprints suggest a common theme. Spacetime is not fundamental, and locality is a reliable approximation, not an axiom. Strings hint that ultraviolet behavior is softened by extended objects and hidden dimensions. Loops hint that geometry has discrete spectra, and that singularities can dissolve into quantum transitions. Holography hints that the deepest description may be informational, with geometry emerging from entanglement. Next, we turn from blueprints to probes. If the Planck wall is real, we still look for cracks where it leaves a measurable trace. The universe may not let us touch the wall directly, yet it may let us hear it, faintly, in cosmic patterns, in gravitational waves, or in the entanglement of carefully prepared masses. The Planck scale has sounded like a distant wall, but walls cast shadows, and shadows can be measured. If quantum gravity is real, it should leak clues into experiments and into the sky. Faint, indirect signatures that survive ordinary noise. This final chapter closes the arc by moving from blueprints to evidence, then back to the central question. Chapter 3 framed the hook as an operational trap, almost like a riddle posed to nature. Ask for finer localization, and the universe can answer with a horizon, because energy used to probe a point also gravitates. Chapter 5 reframed that trap as bookkeeping, where the accounting rules of quantum theory collide with the geometry of black holes. Horizons threaten unitarity unless information and geometry share a deeper quantum structure, one that does not let correlation simply vanish. Now we ask a practical question. Can gravity transmit quantum information in the lab, even when gravity is weak and spacetime looks nearly flat? If it can, then gravity is not only a classical curvature field that passively shapes trajectories. It is a quantum mediator with a channel capacity, able to carry phase information rather than mere statistics. The tabletop idea is simple to state and hard to execute, which is often how physics advances. Prepare two small masses so each one occupies a spatial superposition, meaning the same object is coherently here and there at once. Let them interact only through their mutual gravitational field, with every other force suppressed below detectability. If the final joint state is entangled, gravity must have carried non-classical correlations. Visually, the scene is almost austere. Two tiny spheres hang in darkness, isolated inside a vacuum chamber that looks more like a spacecraft component than a laboratory tool. Lasers trace thin paths through viewports, while vibration stages float the entire apparatus like a ship on calm water. In that quiet, the experiment tries to hear a whisper, the phase shift from Newton's constant itself. The logic is sharp because entanglement is not a classical resource, and it cannot be faked by ordinary coordination. Two systems cannot become entangled through local operations and classical communication alone, even if a clever classical signal orchestrates their outcomes. If gravity were only a classical channel, it could at most correlate measurement results after the fact. It could not generate the phase-sensitive structure that entanglement witnesses detect, where interference depends on joint branch histories. This point hides a deeper statement about quantum theory. Entanglement is not just strong correlation, because classical variables can also correlate strongly. Entanglement is correlation in complementary bases, where the joint state cannot be written as a mixture of independent local states. That is why the proposed experiments focus on witness inequalities and basis changes, because the signature lives in coherence, not in averages. Candidate setups start with micro or nanoscale masses, often dielectric spheres, levitated particles, or patterned resonators engineered for low loss. Each mass is placed in a superposition of two locations using interferometry or spin-dependent forces, so the center of mass itself becomes a quantum variable. The separation is small but controlled, so gravitational coupling is weak but calculable, using the Newtonian potential as a leading approximation. The interaction time is long enough for a gravity-induced phase to accumulate, but short enough that the environment does not steal the coherence. In the simplest picture, each mass has two branches, left and right, and the pair has four joint branch configurations. Gravity assigns each configuration a slightly different potential energy, because the distance between masses depends on which branches are occupied. Over time, those energy differences translate into relative phases, and relative phases are the currency of interference. If the phase depends on both masses' branch choices, the final state cannot be written as a product. Entanglement becomes the natural outcome. One common blueprint uses an interferometer for each mass, essentially a split path device for matter rather than light. Each interferometer splits the wave function into two paths, then recombines it with exquisite phase stability. Gravity adds a relative phase that depends on the path pairings, so the recombination fringes encode the mutual interaction. If the phases depend on both masses' branch choices, the output statistics can violate separability, which is the operational definition of entanglement. The visual language here is clean and geometric. Animated paths separate like a tuning fork, then curve back together as if guided by invisible rails. Overlaid numbers mark tiny phase angles, accumulating slowly like the hand of a clock. When the paths reunite, interference fringes appear, bright and dark bands that shift by fractions of a cycle, revealing an interaction too small to feel directly. Another blueprint couples a mass to an internal degree of freedom, like a spin, because spins are easier to manipulate and measure with high fidelity. The spin controls the mass position, creating a position-superposition conditional on spin state, often through magnetic gradients or engineered forces. Two such systems interact gravitationally, then spins are measured in different bases. Entanglement between spins becomes a proxy for entanglement between masses, translating a spatial effect into a qubit-like readout. This proxy matters because it turns a delicate mechanical question into a cleaner information question. Spins can be rotated, echoed, and read out with techniques borrowed from atomic physics and quantum computing. That allows the experiment to test correlations along multiple axes, which is exactly what entanglement witnesses require. In effect, the masses do the gravitational interaction, while the spins serve as the interpreters. The experimental enemy is not subtle theory. The enemy is decoherence, the rapid loss of phase coherence to the environment, which turns a superposition into an ordinary mixture. Thermal photons can scatter and record which path information, even when the light is unseen. Residual gas collisions can kick the mass and randomize its phase, one molecule at a time. Vibrations, acoustic noise, and patch potentials on surfaces can all mimic or overwhelm tiny gravitational phases. Patch potentials deserve special attention because they are treacherously ordinary. Even a neutral object can carry microscopic variations in surface charge, producing stray electric fields that fluctuate with position. At micron separations, those fields can dominate gravity by many orders of magnitude, and they can drift over time. The experiment must isolate the masses from electromagnetic noise so completely that gravity becomes the dominant remaining interaction, which is an extraordinary standard. Isolation requires cryogenic temperatures, ultra-high vacuum, and careful materials chosen for low dielectric loss and stable surfaces. It also requires shielding and grounding to suppress stray electric fields, sometimes with nested Faraday cages and carefully routed cables. Magnetic impurities must be controlled if spins are used, because a single defect can create noise at the relevant frequencies. Mechanical vibrations must be filtered so path separations remain stable over the interaction time, often with multi-stage suspension and active feedback. There is also a subtler form of isolation from measurement itself. If any sensor learns which branch a mass occupies, even indirectly, coherence is lost. That forces the experiment to delay readout until after the gravitational interaction, and to keep monitoring signals below the witch path threshold. In quantum language, the environment must not become entangled with the branch label. The gravitational signal is small because g is small, and because the masses must remain quantum objects rather than classical test weights. The phase scales with mass, separation, and time, but increasing any of them increases decoherence risk. Larger masses couple more strongly but are harder to cool and harder to keep in a low-entropy motional state. Larger separations increase phase but also increase sensitivity to fields and vibrations, which grow more dangerous with distance. Longer times help but invite environmental entanglement that washes out the effect. This trade-off is the heart of the engineering problem, and it is why proposals often look like careful compromises. The masses must be heavy enough to feel each other gravitationally, yet light enough to be placed in coherent motion. The superposition must be wide enough to create distinguishable branch distances, yet narrow enough to avoid uncontrolled forces. The interaction time must be long enough to accumulate a measurable phase, yet short enough to outrun decoherence. So what would count as evidence? The clean target is an entanglement witness that rules out all separable states, consistent with the data, not merely a suggestive fringe shift. In practice, that means measuring correlations in multiple bases, not just one, and showing that a classical mixture cannot reproduce them. It means demonstrating a violation of a bound that any classical mediator model must satisfy, with error bars that survive skeptical scrutiny. A second target is a phase shift consistent with Newtonian gravitational coupling between the superposed branches, because Newton's potential is the leading weak field limit of general relativity. The phase must scale with distance and mass exactly as predicted, within uncertainties that include calibration and drift. The scaling matters because it distinguishes gravity from hidden electromagnetic couplings, which often scale differently with separation or material properties. It also constrains exotic modifications that would change the potential at short range, such as Yukawa-like corrections. A third target is ruling out classical channel explanations, which is harder than it sounds because hybrid theories can be slippery. Some hybrid models treat gravity as classical, but sourced by quantum expectation values, so the field responds to averages rather than branch realities. Others allow measurement-like collapse induced by gravity, effectively turning gravity into a noisy observer. The experiment must show that no model with only classical communication between the masses can reproduce the observed entanglement witness, given the measured noise and the allowed loopholes. Historically, this is a modern echo of older debates about what must be quantized. In the early days of quantum theory, fields like electromagnetism were first treated semi-classically, then forced into full quantization by experiments and consistency. Gravity has resisted that pressure because it is so weak at the scale of atoms and photons. These tabletop proposals are designed to apply the pressure directly, using quantum information as the lever. Even a successful result would not reveal the full ultraviolet completion, and it would not choose strings over loops or holography. It would not tell us whether spacetime is built from vibrating strings, discrete spin networks, or entanglement patterns in a deeper theory. But it would answer a foundational yes or no question, one that has hovered for decades. Does gravity itself carry quantum information, or is it an emergent classical bookkeeping field? Now we widen the search beyond entanglement, because quantum gravity could also show itself as a deformation of familiar laws. If Planck Scale structure modifies gravity, it might leave small deviations from known behavior at accessible distances, especially where backgrounds can be controlled. Precision tests of gravity at short range look for departures from the inverse square law, which is the geometric fingerprint of three spatial dimensions. They also look for Yukawa-like new forces that could come from extra dimensions or light scalar fields. These experiments use torsion balances, microcantilevers, and resonant sensors, each tuned to detect forces that are almost unimaginably small. They measure tiny forces between carefully shaped masses at millimeter to micron separations, where gravity is weak and surfaces dominate. The challenge is again backgrounds, especially electrostatic forces and Casimir forces, the quantum vacuum pressure between conductors. Those backgrounds can be larger than gravity by many orders of magnitude at short distances, which forces meticulous modelling and subtraction. In visuals, the apparatus looks like precision sculpture. Gold-coated plates hover close without touching, and a torsion fibre twists by angles smaller than a human hair's width at arm's length. Graphs overlay the scene, showing force versus distance on logarithmic axes, where gravity is a thin line near the bottom. The drama is in the residuals, the tiny difference between what is measured and what is expected. The payoff is broad constraint power, even when the result is null. If extra dimensions exist and are large enough, gravity could strengthen at short range because flux lines spread into additional directions. If new particles couple to mass or barrier number, they could add a fifth force with a characteristic range set by the particle's mass. Null results carve out parameter space and eliminate whole families of models, turning speculation into a map of what cannot be true. Some searches target violations of the equivalence principle, which is the conceptual spine of general relativity. If different materials fall differently, gravity is not purely geometric in Einstein's sense, because geometry does not care what an object is made of. Atom interferometers and satellite experiments compare accelerations with extreme precision, using matter waves as rulers and clocks. Any composition dependence would point to new fields or new couplings that quantum gravity models sometimes predict, especially in scenarios with light scalars. Other searches test Lorentz invariance and dispersion, because spacetime symmetries are often where new physics first leaves a trace. Some quantum gravity ideas predict energy-dependent speeds of propagation, or modified commutators, or preferred frames that emerge from microscopic structure. High-precision clocks and interferometers can bound such effects by comparing frequencies over time and orientation. The bounds are often so strong that only very suppressed Planck scale violations remain viable, which is itself a clue about how carefully nature protects symmetry. Now we move from the lab to the sky. The universe provides strong field gravity and long baselines that no experiment can build, and it supplies them continuously. Gravitational waves are a new probe of dynamical spacetime, not just static curvature, and they carry information in their phase evolution. They test general relativity in regimes of high velocity and strong curvature, where the theory's nonlinear character matters. The inspiral phase checks the nonlinear structure of Einstein's equations in a controlled way, because the system evolves slowly enough to model accurately. The waveform encodes how energy and angular momentum radiate away, and how the orbit tightens as a consequence. Deviations could signal extrapolarizations, massive gravitons, or modified propagation that changes arrival times and phasing. So far, the observed signals match general relativity within current sensitivity, which already constrains many alternatives. The merger and ring-down probe horizon-scale physics, where the geometry is most extreme without becoming singular. After two black holes merge, the remnant rings like a damped oscillator, and the signal becomes a superposition of quasi-normal modes. The quasi-normal mode spectrum depends on the near-horizon geometry and boundary conditions, much like how a drum's tone depends on its shape and tension. If horizons are replaced by quantum structure, the ring-down could shift or include late-time echoes. Echo claims are difficult because detectors are noisy, and templates are uncertain, especially in the late-time regime where the signal is weakest. A small modelling error can look like a new effect, and a statistical fluctuation can masquerade as a pattern. Still, the logic is compelling because the ring-down is a clean regime, governed by a small number of parameters if general relativity is correct. That makes it a natural place to search for small, systematic departures. Strong field tests also connect back to the information paradox, not by solving it directly, but by probing its stage. If information escapes through subtle, non-local correlations, the near-horizon region might differ from a perfect absorber, even if it looks classical at coarse resolution. That difference could alter reflection properties for perturbations, changing how waves scatter and decay. Any measurable deviation would be a rare bridge between quantum information and astrophysical data, linking thought experiments to observables. There is a quiet question behind these searches. If the horizon is not a fundamental one-way membrane, what replaces it in the microscopic description, and how would that replacement reveal itself without violating known physics? Could the deviations be encoded only in correlations that are hard to extract, rather than in obvious distortions of the waveform? The mystery is not that we have no answers, but that nature may have chosen answers that are subtle by design. Now we push farther back in time. Cosmology offers a different amplification mechanism, because the early universe acted like a giant microscope that enlarged quantum fluctuations. The early universe stretched microscopic quantum fluctuations into macroscopic structures, seeding galaxies and the pattern of the cosmic microwave background. If quantum gravity modified the initial state, or the dynamics at extreme energy density, it could leave relic patterns that persist as statistical fingerprints. Primordial gravitational waves are the cleanest target because they interact weakly after production, and they propagate almost freely through cosmic history. Inflation, if it occurred, would generate a stochastic background with a spectrum tied to the inflationary energy scale. Detecting that background would not reach the Planck scale directly, because inflation could occur below it. It would constrain physics at energies far beyond colliders and close to grand unification, where quantum fields and gravity begin to share the same stage. The cosmic microwave background already constrains many possibilities, and it does so with a precision that would have seemed impossible a generation ago. Its temperature, anisotropies, and polarization encode the statistics of primordial fluctuations, including their amplitude, tilt, and correlations across scales. Non-Gaussianity, running spectral indices, and tensor-to-scalar ratios all limit early universe models, and they limit how much room quantum gravity corrections have. Quantum gravity corrections must hide within these tight bounds, or else they would already have announced themselves. Some models predict specific Planck-suppressed signatures, which are small by construction but not always hopeless. They include modified dispersion relations for primordial modes, or transplanckian initial conditions where modes begin smaller than the Planck length. They also include small violations of locality that could alter phase relationships across scales. The difficulty is that many effects are degenerate with mundane astrophysical parameters, like foreground dust or Orionization history. and that degeneracy can blur interpretation. Even when the data do not point to a unique microscopic story, they can still be decisive. If a proposed correction would have produced a detectable oscillation in the power spectrum, or a specific non-Gaussian shape, it can be excluded. If a model predicts too much tensor power, it can be pushed into a corner or ruled out. In that sense, cosmology acts like a sieve, letting only the most carefully consistent ideas pass. This is the pattern across all windows, and it is why the search feels both frustrating and profound. Direct access to Planck energies is unlikely, perhaps forever, because the Planck wall is built from constants, not engineering limits. But indirect consistency conditions can be ruthless, and they can be more informative than a single spectacular anomaly. They can eliminate models that would have produced detectable violations of known symmetries or known spectra, leaving behind a smaller, sharper space of possibilities. So the strategy becomes triangulation, a method as old as navigation and as modern as data science. Tabletop experiments ask whether gravity is a quantum channel, capable of entangling otherwise isolated systems. Precision gravity tests ask whether new degrees of freedom modify forces at short range, where deviations could hide. Astrophysics tests strong field geometry and propagation, where horizons and curvature are unavoidable. Cosmology tests the earliest boundary conditions and the quantum origin of structure, where initial assumptions are written into the sky. Each window is partial, but together they map the space of possibilities, and they cross-check one another's blind spots. A quantum mediator result would kill purely classical gravity models, because classical channels cannot produce the required entanglement. A short-range deviation would point to extra fields or dimensions, suggesting new ingredients beyond Einstein's geometry. A ring-down anomaly would target horizon-scale structure, where information questions become physical. A primordial tensor detection would anchor early universe energy scales, tightening the link between quantum fields and gravity. Now we synthesize the story's threads. Singularities were general relativity's error messages, places where curvature becomes infinite and the equations stop making sense. The information paradox was quantum theory's refusal to erase, insisting that unitary evolution preserves information even when gravity seems to hide it. Spacetime foam was the warning that geometry fluctuates when energy fluctuations gravitate, making the notion of a smooth manifold suspect. All point to the same missing ingredient, the quantum structure of geometry itself. The blueprints in Chapter 6 offered candidate languages, each with its own grammar and its own promises. Strings soften ultraviolet behavior and tie gravity to quantum consistency, replacing point particles with extended objects that smear interactions. Loops quantize geometry and suggest bounces instead of singularities, turning areas and volumes into discrete spectra. Holography and entanglement suggest geometry is emergent from quantum information, where spacetime is a code rather than a container. In different ways, they all treat spacetime as not fundamental. Experiments now pressure those languages, not by confirming their full machinery, but by testing their shared commitments. If gravity entangles, then geometry must support quantum coherence, at least in the weak field regime where the experiment operates. If area laws and unitarity hold, then horizons must be coarse-grained descriptions, not absolute erasers. If strong field observations keep matching general relativity, then quantum corrections must be subtle or encoded in correlations, not in gross violations. If cosmology keeps tightening bounds, then early universe quantum gravity must respect observed statistics, even while rewriting the microscopic story. This returns us to the central question: why do quantum mechanics and general relativity fail at the Planck scale, and why does that failure feel structural rather than accidental? They fail because each assumes a different meaning of space and time, and those meanings cannot both be fundamental. Quantum theory assumes a fixed stage with a reliable clock, so probabilities evolve against a background that does not fluctuate. General relativity makes the stage dynamical and turns energy into geometry, so the clock and ruler become part of the system. At the Planck boundary, measurement, geometry, and uncertainty become the same problem, and the separation between observer and observed becomes ambiguous. Trying to define a point demands energy, because shorter wavelengths require higher momenta. That energy curves space-time and can create a horizon, which hides the very region being probed. The act of asking for more precision changes the causal structure that would define the answer, turning epistemology into geometry. So the Planck scale is not only a tiny distance, and it is not merely a number written in units. It is a boundary of description, where our usual variables stop being operationally anchored to procedures we can imagine performing. Crossing it may require redefining what space is and what time is, and what it means for information to be localized. The question becomes not only what exists, but what can be asked without contradiction. We end where the documentary began, with the hook as a principle. There is a boundary in nature where sharper questions do not yield sharper answers, because the tools of sharpness become gravitational sources. They can make the universe answer back with a black hole, turning a measurement into an event horizon. But the boundary is also an invitation, because boundaries in physics often mark the edge of an old language. If space-time is emergent and quantum-coded, then horizons, entanglement, and cosmic relics are parts of the codebook, scattered across scales from laboratories to galaxies. The next revolution will not be a bigger collider, because the wall is not one of budget or size. It will be learning to speak the language that replaces space and time when the page itself becomes quantum, and when the shadows of the Planck wall finally resolve into evidence. Across this journey we kept shrinking the ruler, trading longer wavelengths for shorter ones and gentler questions for more violent probes. Quantum mechanics demanded higher momenta for tighter localization, while general relativity insisted that concentrated energy becomes curvature, and curvature can become a horizon. The Planck Scale emerged as the unique seam stitched from C, H and G, where Compton wavelength and Schwarzschild radius meet, and the very act of measurement back-reacts into geometry. From there, the smooth universe we usually trust began to fray. If vacuum fluctuations are real enough to shift atomic spectra and push plates together, then at extreme resolution those fluctuations must gravitate, turning the background into a participant. Space-time foam, virtual trapped surfaces and jittering light cones stop being poetic metaphors and become warnings that locality and even before and after may be scale-dependent approximations. Black holes then sharpen the lesson into a paradox with teeth. Horizons behave like thermodynamic objects, with temperature and entropy that counts in area, not volume, as if nature keeps its deepest ledger on boundaries. Hawking radiation forces us to ask where information goes during evaporation, and why a low curvature horizon can still expose a conflict between unitarity, locality, and the equivalence principle. The proposed escapes, strings softening the ultraviolet with extended objects, loops discretizing geometry into quanta of area and volume, and holography suggesting spacetime can be rebuilt from entanglement, did not close the case, but they did converge on a theme. What fails at the Planck scale may not be physics in general, but our assumption that spacetime is the stage rather than the script. And the most hopeful clue is that the script looks increasingly like quantum information, written into correlations that can masquerade as geometry when viewed from far away. Finally, we stepped back from the wall and looked for its shadows. Tabletop experiments that try to make gravity entangle two masses, precision tests of short-range forces, gravitational wave ring-downs hunting for horizon microstructure, and cosmological statistics searching for Planck-suppressed fingerprints, all offer ways to learn without smashing directly into the barrier. Even a single confirmed anomaly would not hand us a final theory, but it would tell us which language, strings, loops, holography, or something unimagined, can translate nature's code without contradiction. So why does physics break when we try to look closer than close? And why does gravity enforce the limit like a sensor? Because at that boundary, distance is no longer a passive property waiting to be read. It is a question that costs energy, and that energy reshapes the thing you're trying to define, until an event horizon can form, and the universe answers with silence. At the Planck scale, quantum uncertainty, geometry, and measurement collapse into one problem, and the failure is the clue. It suggests spacetime is not hiding a smaller piece of smoothness, but a different kind of reality, whose fundamental degrees of freedom are not points, but relationships. If information really does survive horizons, if area really does count what volume cannot, then space and time may be what quantum systems agree upon, not what they live inside. The Planck length is not the universe's smallest brick, it is the edge of a map, where the ink becomes the territory, and the territory becomes a code. Watch the next generation of experiments and observations closely, because the first credible crack in the wall may teach us what spacetime has been made of all along.